Yanjun. Yanjun. Oh, inside. Then let's turn this one on too, right?
There you go.
Yanjun, if you are here, Yanjun Chen, if you are here, come talk to us about your testing your slides.
Check. Hello. Good morning.
We're just going to check if the stream is on, and then we're going to get this material interfaces and displays session started. So we're just waiting for YouTube. I think we're one click away from start. All right, we are live. That's the good news. We got the thumbs up. So very excited to be sharing this session. My name is Pedro Lopez. I work at the University of Chicago. This is the Material Interfaces and Display session, and I think it's really one of the coolest sessions of UIST. Zero papers in this session, so I'm unbiased here. But really, what is so interesting here is that we're at the intersection of sort of be very clever about how to organize materials, be very clever how to organize haptic actuators, be very clever how to reconfigure things to create new haptic experiences, new devices, new sensors even, and I think it's going to be a real treat for everyone to see these papers. I also just want to tell you that I think you all know the drill by now, since it's our last day, but of course, we're going to have the talks, 1 or 2 minutes, 2 minutes for questions, meaning 1 or 2 questions, depending on how long you are asking your question. And you could come up to the microphone. I'm going to leave this one here, but if you just raise your hand, one of our session SVs are going to bring the microphone to you. So as you want. You can also ask questions on Discord. We have that thing here live to us. So, I know it's the last day and we're a little bit tired, but at the same time, it's the last day, so it's one of your last chances to engage and ask questions. So, make advantage of that. And this is an awesome session. The first paper we're going to hear about is reconfigurable elastic metamaterials. This is work done by Willa Wang, presenting work that she did at Carnegie Mellon University. With her co-authors Yumei Chuang, Luke Darcy, Grace Liu, and Alexandra Ion. So let's give a round of applause for Willa.
Thank you. Good morning, everyone. My name is Willa. I'm currently a first-year PhD student at the University of Chicago. I'm happy to present our work, Reconfigurable Elastic Metamaterials. This was done during my master's study at Carnegie Mellon in collaboration with Yumeng Zhang, Luke Darcy, Grace Liu, and Professor Alexandra Ion. So here, the user is going to drop 2 balls onto the material. And you can see that those black lists split the material into different sizes. And when the ball drops onto those different areas, the material will give different bounce heights. To configure this elastic response, users just need to snap this black configuration list they printed onto the yellow generic material to activate certain cells. The material can be easily configured for different things. Users just need to cut the material into size and configure the pieces. Here, the user is making 2 VR props out of 1 single piece of material. And in this VR scene, 1 prop can be used as a hand pump for users to squeeze to resize the screen. And another prop can be used as a remote control to adjust the volume. So this snippet of workflow really shows how users can take a generic material and configure it to be different things very easily. So what is the motivation behind this work? Manufacturing technology such as 3D printing has allowed end users to easily fabricate objects with custom shapes. Taking advantage of this, researchers have started to go beyond always rigid objects and started to add different material properties into them. So in this case, for example, the microstructures around the joints changes local stiffness to allow bending of that character. Such artificial microstructure materials are often known as mechanical metamaterials. These materials' internal structures can be designed and can offer greater space for customizable material properties. So for instance, the material can be designed to have the shock-absorbing internal structures that protect the egg on the left from breaking. These mechanical structure also allows materials to be seen as machines that take an input motion and transform it into an output motion. Some metal materials can exhibit programmable stiffness, but also mass fabricatable. However, current programmable materials are usually designed entirely in software and provides very limited room for customization once they are fabricated. This workflow often results in predefined and one-off designs, which means that user can't really tune the material properties when they're tangibly interacting with it. So what about we swap this order? What does it look like when users can customize material after fabrication? This might sound a little bit abstract, but it would not be too unfamiliar to you, because in fact, this is actually how many users usually interact with materials. They take a generic stock material that is accessible, such as plywood, foam, fabric, etc., and customize as they interact with it. And we would like to think of metal materials as a generic stock material that end users can just purchase and have access to. We're also pushing the boundary of the functionality of stock materials by designing them with programmability in mind. To this end, we propose a novel design for elastic materials that are reconfigurable by end users after fabrication. Conceptually, we decompose our material into a complex macrostructure material that is generic and a simple configuration mechanism that users can just print at home. Our generic material consists of two types of cells. First type of cell is spring cells. We design the cell structure to store elastic energy, and we enhance this feature by having thicker edges of the oval structure of the cell. The other cell is damper cell, and then we design it to absorb energy. So here, the cell edge will slide against the corrugated wall to create dry friction. And that's how energy is dissipated. The legs are also tuned to be just elastic enough to push the top back out to enable repeated damping. And we designed the spring and damper cells to be opposite in a sense, as one returns energy and the other dissipates energy. We then arrange these two opposite cells in this checkerboard pattern such that they can be coupled in parallel to allow fine-tuning of local elastic response. So how does the cell coupling work? As the lid is snapped on, the cells are selectively activated. So here the spacer underneath the flat lid will press down the cell underneath them to activate the cells, while leaving other cells unaffected and not activated. And users can print and select different configuration lists and repeatedly configure the generic material. To help users create the configuration layers for desired elasticity, we also implemented an interactive editor using a custom prediction model. So on the left, users select regions of the material. And then the slider on the right-hand side would take a mass and target bounce height, which trigger the computation of active cells. And users can preview and adjust the ball bouncing. And when the user changes the target height, the configuration also updates, which activates a mixture of spring and damper cells. To formulate our prediction model, we measure the drop height and the bounce height of an object and to calculate the energy loss. Here's our experiment setup. And we model the spring damper mixture system as a damped harmonic oscillator. And we build up our model from a simple mass spring damper system. So here Q is a commonly used quality factor Q that reflects how well an oscillating system preserves energy. As we care about the loss of energy, we model this decay using Q inverse, as shown on the screen. Here the B is the damping constant, and K is the spring constant. This is for a single spring and cell pair. And since our system has many springs and dampers coupled in parallel, we approximate the system such that the unit cells share the same conformation, and therefore the force acting upon the dropped mass during collision will be the sum from all spring and dampers combined. As a result, the aggregate spring and damping constants are the sum of their individual spring and damping constants. Please refer to our paper for more details, but this is the mean of our formulation. And over all data points, we obtain a relative approximated residual of 3%. That means that by taking a target bounce height and a mass, our system will be able to calculate the number of springs and dampers that should be activated. And this formulation allows a generic material to be programmable through the configuration mechanism that we designed. So our material can be in play to make different passive VR props. So here we show a living room VR scenario where all the passive props are made from our material. The hand pump and remote control that you have seen earlier, and the sofa material. So the user is sitting on our larger scale sofa material that simulates the softness of sofa. And when the user starts watching TV, they can squeeze the hand pump that they previously made from our material to resize the screen. Here the spring cells are coupled to have that elastic haptic. And user can also tilt the remote to adjust the volume. So here the cells in the center are activated to act as pivot points to allow tilting effect. Another application can be a reconfigurable shoe sole. Here the shoe sole is optimized for volleyball playing that involves a lot of jumping. So we activate more springs on the heel to help with that. And if users like to do different physical activities, they can customize and change the shoe sole to best accommodate those. So now the shoe sole is quickly adapted for a long distance running, where the shoe sole have a different configuration. A piano with adjustable key stiffness can also be made. Here the user swaps out one of the keys he found too rigid and can play the piano. Users can also create their own game on our large-scale material. Here is a battle-shaped like ball game that we created. The goal of the game is for a player to catch more balls that bounce from the material than their opponent. Before the game starts, player will configure their opponent's side such that they know how tall or low the ball will bounce while their opponent doesn't know. So here this user catches the ball, but when he throws his back, the other user didn't catch it because I didn't expect how low the ball bounced. And users can customize their game repeatedly. To sum up, today we introduce you to this reconfigurable elastic metamaterials, which has two parts: a generic complex industrial fabricated material and a simple configuration mechanism that is easy to fabricate by end users. We kept end users in mind when we designed the material and its configuration mechanism. The configuration is simple and repeatable, as user can just snap the lid onto the generic material. The generic material is highly customizable, as user can cut it into custom shapes for different applications. Last but not least, we want to emphasize that we deliberately distinguish the complex generic material intended to be industrially manufactured from the simple configuration mechanism that users can print. This concept is intended to take the majority of the fabrication load, here the complex material, off the user's shoulder. That will save users a significant amount of time, as they can just purchase the generic stock material and only need to take care of the configuration part. This work also aligns with the prior works that makes material customization from predefined to user transformable to user reconfigurable. And this work is one step we took, and we focus on one material property in this vision of making metamaterials accessible to end users and pushing the boundary of stock materials. In order to reach that vision, future work needs to be done on miniaturization of the cells, on allowing reconfiguration when the material is wrapped around objects, and also larger mass range, etc. So that's the end of my talk. Thank you so much for watching. I'm happy to take questions.
Work and how you're like have this really hands-on dynamic model with stiffness and damping.
Thank you.
Easy question: did you think about incorporating mass and inertia into this, and like how would you go about changing the resonance or changing the dynamics by adjusting the mass?
So within the scope of this work, we only tested the elastic response when objects are dropped onto the list, and then there are different kind of bounce heights as the mass changes as well. For example, larger mass will just have more energy loss compared to smaller mass. But yeah, but that's a great point. Definitely one of the interesting future works. Yeah.
Hi, Doan from MITCC.
Hi.
Great talk, and I also love the applications for VR. I was wondering if you thought about integrating electronics into these prototypes, like for some of the applications that you showed. I think you didn't. Were there any sensors? I guess.
Yeah, that's a great point. I'm glad you asked. So for the VR example, we use the Oculus built-in hand tracking. So there's no electronics in the sensors in the material, because we want it to be kind of generic and easy.
And if you wanted to integrate electronics, like would you put it in the bottom base, the yellow part, or the black part, or both? Depends on the application, I guess.
Yeah, I mean, if you want the electronics to be applicable for most of the applications you probably want it to be on the generic part. But the customization is done on the configuration list, so that part you can just freely use anything you want to customize.
Thanks so much.
Yep.
Hi, Yudai from University of Chicago, great talk here. I was wondering, is it possible to extend your device to curvature surfaces, like non-flat surfaces, by just changing the shape of the configurable part, like the wrap part of the thing?
I think for this work, we focus on configuration on the flat lid, but right now with the current configuration material design, it is possible to wrap it around cylindrical surfaces and then do the column-wise configuration. But yeah, wrapping around objects is definitely one of the future works.
Hello, Marwa from MIT Still, very cool talk. So I was just wondering, in terms of the applications that you had, a lot of them seem to be going through like cyclic deformation. So was this something that you looked into in terms of how many cycles can it go to through like, without like necessarily reaching fatigue in terms of like the material?
Yeah, great question. So the material uses TPU Ninja Flex, and it's very tough. It's 660 elongation at break. So it's very tough elastomer. And then the material is designed to be kind of in its rest shape when it's not being used, so that kind of also mitigates the fatigue. And during the 2-3 months of experimentation, we didn't observe any significant changes in performance. Great question. Thank you.
Let's thank Will one. All right. Roland's totally ready. He's going to talk about this new type of sensor called SpaceR. I was reading the paper last night, and it's amazing. Roland, Mira, and Michael Haller, who's here as well, are from the University of Applied Sciences in Alba, Austria. I just want to make a very quick mention that Michael is looking for more folks to join this adventure of building these incredible things that he does. So if you're a student, PhD or postdoc, I believe, right, that is really excited about this work, I think you should talk to this person over there. Go for it.
Thanks, Pedro. Good morning, everybody. Actually, no.
It's already on.
I have 3 mics now. Okay. I prefer not to. Okay, again, good morning, everybody. Welcome to this talk with the title SpaceR, which is the name of our of our ready-made tactile and highly responsive knitted UI elements. And to give it away already in the beginning, this the uppercase R is referring to the electrical resistance, since we're doing resistive sensing here, which enables the continuous input. My name is Roland Eigner, and this work has been done in collaboration with my colleague Mira Hauerfellner and with Professor Michael Haller. First, I would like to talk a little bit about our motivation. One of the main advantages of textiles over sensors using other solutions such as foils is that they are breathable and usually very, thanks, and usually very comfortable to wear on skin. Knitted fabrics, furthermore, have the advantage of being highly elastic since they are composed of loops. In weaves and non-woven structures, such as felts, on the other hand, the fibers are going straight, and as a result, a knit can be draped more easily, and, for example, as covers for furniture. As you certainly will know, several other researchers have already explored integration of sensing electronics into textile, for example, for capacitive touch sensing in weaves and knits using conductive yarn, or by adding functionality to pre-existing textiles, for example, by treating with polypyrrole or by adding, by coating with carbon. For us, however, the most interesting aspect of weft knitting machines is that you have precise control at loop level, which enables you really to create intricate surfaces. And furthermore, you can combine many different materials already at fabrication time, which enables you to create ready-made knit sensors that do not require any post-processing. And in fact, professional knitters already do this nowadays. They combine numerous materials and advanced structures to create knits with very interesting physical properties. And one example for this are spacer knits. I suppose most of you won't know the term, but I'm fairly certain that everybody had already contact with them. Spacers are composed of two opposing knit faces that are connected by a rather stiff nylon monofilament that goes back and forth in between in kind of a zigzag. Depending on the nylon, the result can be highly compact when used for shock absorbers or protective gear, or it can be rather soft when used as for upholstery, for example, as a substitute for foams. The way this works is that the nylon is inserted by the knitting machine when the fabric is extended. And when the fabric comes out of the machine, the faces shrink, which causes the filler to stand up and push the two faces apart, which provides a special haptic characteristic. Note here that the length of the nylon filler segments is unchanged, and this also means that the more the faces contract, the thicker the structure will be then in the end. Others have already said a great deal about spacers. Most notably in the extended community here, I would refer to the work of Leah Alba, probably mispronouncing this, sorry Leah, and others which analyzed manufacturing parameters mostly regarding to structure of the nylon monofilament and its effect to mechanical properties. Examples of those manufacturing parameters are amount of nylon inserted and size and offset of the zigzag courses. We build on top of her work and add shaping and UI functionality. Due to limited time here, I will be focusing mostly on these three topics. And as always, for more details, please refer to the paper. First, fabrication. How can you knit a spacer? Unlike a usual balanced spacer fabric, we want a distinct bulge on one side, which will provide our tactile UI element, which makes it also great for ice-free interaction. We achieve this bulge by using 100% of spandex on the back face and plain polyamide yarn on the front face. This causes the back face to contract very strongly, which makes it flat. You also notice that it is really necessary to knit at half gauge, which means you skip every other needle, so the fabric can shrink even more when it comes out of the machine. The front face, on the other hand, is pushed out in the areas where the nylon is inserted. We further reinforce this effect by increasing loop size in this area, so the PA can yield even more. We do not add any nylon beyond the UI element. Instead, we connect front and back faces there so they hold together. Along the contour, we interlock to create a distinct and compact outline. Now for rapid prototyping and fast iteration, we created a fabrication pipeline that starts from image files which encode our structures. From those image files, we generate our knitting programs using scripts. And you can find the code on our GitHub if you're interested. Our software is based on the knit-out file format and libraries by Jim McCann from CMU, and is therefore machine independent. So we generate human-readable knit-out format that allows for further manual edits and for visual verification. Knit-out is then converted into machine-specific format that is imported into SIGCHI knit paint in our case, and then sent to the machine for fabrication. For visualization and conversion, we use tools provided by the CMU Textiles Lab. Second, sensing. How would you turn them into sensors, and how can you really use them as UI elements in the end? Our spacers are based on the well-known force-sensitive resistors, or FSRs in short. In FSRs, two conductive surfaces are in contact with a resistive film, and when they are compressed, the contact area rises and the electrical resistance drops. We do something similar. In our spacers, the filler is not just nylon. Instead, it is combined with a resistive yarn, and electrodes are knit on either side using conductive yarn. When the filler is now compressed, the number of contact points within the filler is increased, and the resistance drops. As you can see here, we use yarn with highly different conductivity. We do this so the resistance ratio between sensor area and connector area or connector trace is maximized. Otherwise, deformations on the connectors would also contribute to the measurement, and we don't want that. The result is highly responsive and shows very little hysteresis. We evaluated our sensors by varying manufacturing parameters, such as PA loop length, filler spacing, and filler density. And as you can see here on a timeline with 4 actuations up to 20 newtons, in most of our variations, the connectivity G is very much in line with the applied force F. This here is raw measurement data, by the way, without any filtering applied. Third, UI design. What could you possibly do with them, and what are your design opportunities? We created this overview of a design space that includes the dimension of size, thickness, shape, cross-section profile, and firmness. For example, it turned out that by varying manufacturing parameters, you can control the shape of the cross-section profile. You can achieve elements that are mostly more rectangular by increasing the front face loop length, or you can make them considerably higher by increasing the filler spacing. You can find some more of these findings in the paper. Furthermore, you can create a great deal of different shapes and combinations, and we implemented a few here. First, a dual button, very easy to fabricate. We combined 2 different sizes that would symbolize different functions, such as up-down or increase-decrease. Since you can feel the different heights and different sizes, you can very easily make use of them even without having to look at them. With some basic signal processing, we extracted temporal data also in this demo, and from that added another layer of functionality. We mapped slow actuation to one mode of input and fast input to another mode. So with 2 buttons here, you basically have 4 channels of continuous input. Second, we included 2 separate responsive areas into one single element, including tactile separation in between. For that, we obviously require another pair of electrodes. We went for a diamond shape, so you can actually feel the arrows pointing up and down. The result is this kind of a rocker button, and you could imagine using this for up-down control, for example, for scrolling documents or for the window lift in a car. However, note that you have continuous input here, while the window lift only requires binary input, which is on and off. So scrolling is probably a better use case here. since you can also adjust scrolling speed. And what's also nice is that you can perform this kind of micro gestures by tilting finger slightly up and down, and the notch in the middle helps in aligning the finger at equilibrium. Third, we created this 4-way controller, similar to a thumbstick on a gamepad. Here it's getting a bit tricky since we merged 4 interactive regions into one small spacer element. For sake of simplicity, in terms of fabrication, we merged 2 areas for left and right into one. Up and down are electrically self-contained sensors, but for left and right, we merged the grounding electrode. And since our hardware is sampling up, down, left, right, one after the other, and not simultaneously, we can first measure between pins 4 and 5 on the left here, and then between 3 and 5 for right. To reduce further crosstalk, we applied some signal processing steps to get a cleaner signal. And you can find all the extensive description of the signal processing in the supplementary material. The result looks somewhat like a D-pad, but it's actually more comparable to a thumbstick, since it can map pressure to amplitude, for example, to control motion speed. Also, the dent in the middle provides a tangible reference for aligning the finger at the origin. We created this kind of a sock that was pulled over a gear shift grip for this demo here. This was tailored, as you can see, but you can also integrate this controller into a much more complex knit that does not require tailoring. Lastly, let me show you this squeezer controller that we implemented by wrapping a fabric with 4 equally distributed spacers around this handle here. And we saw a use case for this already today. I would like to close with a few takeaways. We demonstrated a multi-material knit that can be fabricated ready-made and does not require post-processing such as tailoring or coding. The element is highly sensitive, highly responsive, and shows good consistency. It is suitable for ice-free interaction and can be extended to multiple sensitive areas. We included the design space and showed how you can control different aspects for their appearance. And as always, there are also limitations, which are mostly inherent from knitting. For example, you are quite limited in shaping, and you have to keep in mind the actual knitting process and what a knitting machine is really capable of. But that's another story. Okay, then thank you so much. This is it for today, and now we should have left some time for questions.
All right. Any quick question here? Or raise your hand and I'll bring this microphone over. If not, I'm going to ask the question that I think is one of the best compliments you can give to a textiles person, which is this looks so already advanced that I'm starting to wonder about things like washability and, can I just have this in my garment and throw it in the dryer? Can you comment a little bit on how far this is on that domain as well?
Mm-hmm. Yeah, washability, we did preliminary washing tests just with one sample, but since washing is not so much of our concern, because we are mostly working not for garments or in the context of garments, we did this on a very limited scale. But the data showed that after 2 or 3 washing cycles, the absolute value of the resistance dropped to about 60–55%. But this shouldn't be of concern, because this is really just absolute resistance, and the dynamic range remains the same basically, so the functionality is still there. Yeah.
Hi, super cool work. Could you comment on the accuracy of the kind of how to measure the deformation, especially for the last example? Could you kind of use your method to kind of measure the deformation in the 3D mesh of the cylinder?
To some extent, maybe. Didn't really try that. I would like to point out that this is meant to be what you can really easily measure is activity, right? I would like to point out that this will never be a measurement device. So it's really not very precise. It's good for providing input in terms of buttons and controllers and these kind of things, but I wouldn't really recommend it for measuring exact values, which would probably be necessary for this use case. but maybe future work.
Let's thank Roland once more.
Thank you.
Right, to the all the speakers, Roland is around, Will is around. You can come talk to them at the end of the session. While Diana is just setting up, I want to also remind you that those QR codes in those doors, they have meaning. You go there, you scan the QR code, or type in the link, and you can vote for the best talk. Maybe it's Roland, maybe it's Willa, I don't know. Maybe it's another session you saw. I would vote for this session. So yeah, you can only vote one time, but please do vote for the best talks. All right. Miang is all set up. He's gonna present work called Kinergy that he's done with his colleagues, both at UW, and he has an announcement at the end that is really cool. So stay tuned for that. Take it away.
Thank you, Pedro. All right, so I'm Liang He. I'm currently work at Purdue University. This work was done when I was a PhD at the University of Washington, in collaboration with my amazing colleagues Xia Shu, Huaishu Peng, Jeff Lipton, and John From Lick. All right, so the talk is about Kinergy, creating 3D printable motion using embeddable kinetic energy. Right, so 3D printing is not a new thing nowadays. And besides static objects, people are starting designing and creating very creative and movable objects such as a green device here. It is a wind-powered energy generator, and or a quadruped with embedded motors, or a hand-cranked sea turtle sculpture, or a prosthetic controlled by external streams. But to create these movable models, we need to have a lot of engineering background, like 3D modeling skills, and we also need to invest a lot of time. Sometimes we need to assemble the parts, and also incorporate the external electronics and some supplies in these 3D printed objects. So in academia, we also have been seeing a lot of researchers exploring this area, like they can embed the joints to make postures, and also they can create a lot of kinematic elements to create these physical animations. And by using a couple of parameterizable kinematic elements, we can actually customize the movement of a one-up toy in an arbitrary shape. Generating vivid movements for the 3D printed objects, and using the external actuators like the motors. And finally, we can actually repurpose kinematic skeletons in arbitrary 3D shapes to achieve desired movements. All right, so in these works, specific kinetic components are used to achieve certain kinetic behaviors. And also to achieve these movements, we usually use some external motors like the electronics, right? You have seen that. And also we can simply actuate it by hand. So my question is, like, can we create custom 3D printable motions using self-contained energy source? My answer is springs. Because springs have the capacity of storing and releasing energy, and spring can be used as a 3D printable energy source to actuate a certain movement in 3D models. And in one of my previous work, I explored how to design and customize 3D printable springs in 3D models. And this work is actually a follow-up of the previous work, and in this work, we try to explore the energy side of these springs. And in this work, we are trying to explore more, not just the helical springs, we also extended it to the spiral spring. So the two questions here I want to answer in this work is how to convert spring movements into various controllable output motion behaviors, and how to lower the barrier for the end user to design and control motion for 3D printing. To answer these two questions, I introduced and also I developed Kinergy. It is an interactive design tool to create self-propelled motion by harnessing the energy stored in the 3D printed springs. To produce controllable motions, we introduced a set of 3D printable units. It's called kinetic units. It is a set of parameterizable designs that use 3D printable springs, compliant locks, and also transmission mechanisms for different motions. One type of these motions is a non-periodic motion, like the instant translation, rotation, and also continuous translation. And another category is called periodic motion. Here it shows continuous rotation, reciprocation, and oscillation, and also the intermittent rotation. Okay, let me show how it works. So first of all, we have 3 parts: spring, and also the lock, and also the transmission mechanism. Here I'm gonna show some examples about the combination of the spring and the lock mechanism. To harness the spring, we have 2 types here, helical and spiral springs. For helical spring, I attach 2 bars to the upper side of this spring, and under the bottom, we attach the compliant latch here. It's like a 3-bar compliant mechanism. So how to do that? So when you press the top part, the bars will go lock in those 2 slots on both sides. And then when you press the button, the 2 slots will move apart, away. And then it will release the bar, and then the whole spring will be extended. This is an animation of this design. For the spiral spring, we also introduced another kind of like lock mechanism here. So we use the ratchet. First of all, we also have the combined latch, and then we have this ratchet gear. So how to lock that? You can press the button again, and the tip of the latch will be locked at one of the gear in the ratchet gear. And if you pull the button, it will release the spring. In life, it looks like this. Okay, so after this spring and lock mechanism, I also want to describe like the transmission mechanism here. So for the non-periodic motion, we don't necessarily need the transmission because we don't need to translate the motion from the spring to the output motion. But for the other periodic motion types, we need to use a certain transmission mechanism here. So first of all, in the transmission mechanism, we use a lot of gears. And how to interface the springs with the gears, we use some mechanisms here. So for the helical spring, we use the rack and pinion mechanism to engage the helical spring and the gear. And for the spiral one, we put the spring and the first gear on the same shaft. So when you turn the spiral spring, the first gear also turns. And beside the gears, we also want to transfer the compression or the rotation of this spring movement to a certain output motion, right? So we introduce and actually use a bunch of different kinematic mechanisms here to achieve a certain desired output. Okay, I'm going to quickly show the structures for these different kinetic units. So for example, here, you have seen one example, which is a very simple cylinder. The yellow part is the end effector, which means you are going to make that move. So later you will see in the tool, we will ask the user to specify the end effector for the movement. And the spring is the main part of this energy source. And for the instant translation, we only have this lock mechanism without a transmission mechanism. Similarly, for the instant rotation, we embed the ratchet gear and the spiral spring in the body. And for the continuous translation and rotation, we actually provide 2 ways to control the energy. So because we are using 2 different types of spring, that gives us the freedom to control the energy in a different way. So first of all, we should convert the body to separate pieces. And for the end effector part, we also use the introduced transmission mechanism part to interface the gear and also the end effector. And later you can actually combine the gears and also the input springs for different control. And the locks will be generated and placed in a position. Okay, I'm going to quickly go through all these things. Yeah, so basically for all this design, we computationally generate all these parts in the tool, which I will introduce later. And then the user has the control to control all these parameters. You can check more in our paper. All right, so I want to introduce the user interface, which is the main part of our tool. So we built this tool using C# and also the Rhino API and also Grasshopper interface. And this is a Grasshopper human UI-based plugin for the Rhino. Here you can see on the left side, it is the Rhino editing scene. And you can create a model from scratch. And here you see the auto-generated log springs and also the transmission mechanisms, which are the gears. And on the right side, this is the interface of our plugin. And the first part, the user can select one particular motion using the kinetic unit. And for each specific unit, we have a unique panel for user to control all these parameters and characterize the motion output. And if you want to see more about how we map these parameters to the output motion and also the design of the underlying mechanism in the model, please refer to our paper for more details. For the last part of this tool, which is motion preview, we use a graph-based representation to manage and generate the motion preview in this implementation. And in this graph, we actually store the part type and parameters in each node, and the edge represents the relationship between these parts. For example, here I show one pull-by car, which uses the continuous rotation kinetic units. So we have these 3 different gear pairs, and all these gears are engaged with each other. And the spring is actually fixed with the first gear, right? And the shaft is also fixed with the spring. Similarly, the shaft is actually engaged with the second gear so that the second gear can rotate around the shaft. And the both shafts are connected to the model, and the last one, the first shaft is actually movable because we use a reference joint to make sure when you turn the spiral spring here, the first gear and the spring, they rotate together. And as a result, the first gear will drive the series of the gears. And for the locking, we have this locking relationship between the latch and also the lock base. So using that graph, we actually can compute and generate this simulation in the tool. Okay, I'm going to show a quick demo about how we use the tool to create this. Like here is the Mr. Halloween pumpkin. So we select the pumpkin body, and then we segment the body, and we can add the spring inside the body, customize the spring, and control the motion characters. And later, once the spring is generated, we can actually add the lock, and then we can print the whole model. And before that, we can actually preview the motion in our preview panel. And here you see I'm changing the spring design by dragging these sliders. This is a result of this pumpkin. Okay, so we identified 3 different types for printing, which we want to make sure the print will be printed in one piece without any manual processing. And here we are using the Automaker Cura Sizer software and Automaker 3 and 3 Extended. The material is PLA and PVA, which is a dissolvable supporting material. And after a series of experiments, we identify the values for these different gaps. I will quickly jump to the application now because I think I'm running out of time. All right, so we made several applications based on these 2. And first of all, it is a self-opening umbrella. And as you can see here, we can actually create a self-opening runner for the umbrella. You can press a button and the umbrella will be opened automatically. And also we can embed electronics in these models. Like this, we can embed an accelerometer, and then we can create a game controller for the Angry Bird game. So you can lock the arm at different position and then controlling the bird in the game. And also we can combine the structure and the electronics for physical device, like the human operated handheld light. And we use a circuit to charge the power, and then the current will be generated and power the light. And also you can customize different parameters for these connecting units to generate different output characteristics. For example, here we create 3 different cars and to show different motion outputs. And finally, we can repurpose the appliance in our home household, and then use the tool to generate a new device for our daily use, like this trash can. All right, I will quickly go through this. So first of all, some limitations that we identify for this work is like the size is very limited because we have a certain size for the embedded structures. So we need to think about other kind of design. And also the printability is really a challenge because sometimes it's very brittle to see how these components are working in real life. And we need to think about more custom triggers to release the energy. And later, lastly, we want to improve the tool for the user to easily use the tool. And also we want to run a workshop to generate more designs with this technology. With that, I want to end my talk. And by the way, I'm hiring students this year. Thank you.
All right. If you have a question, you can just raise your hand. I can bring the microphone, or I'll pass it to this person.
Hello, Sheng Yuan from University of Chicago. This is super cool. I wonder toward your focus mostly on how to release the energy from the spring. Have you explored like how to? I also see some of the application about how to charge back the energy. Can you think about how different ways user can charge back the energy to these mechanisms?
So like restate your question. So you're asking how I can control and recharge the energy through the spring design.
Just for one-time use.
Yeah, so it depends on the application you want to build. Like most of the application I build here is just a one-time use. But if, for example, the flash light example, we can actually keep repeatedly pressing the spring to charge the current for later use. Like I have seen some work about like energy harvesting, like your work. I really like that demo. Yeah, so I think this depends on the application. We just want to provide a platform or infrastructure for the end user to design, customize the application for their use, and the user can decide whether or not they want to do this repeatedly or just a one-time use. Yeah. Hope I answer your question.
Awesome. All right, let's thank Liang once more. This was a really great talk. Again, reminders, you can use Discord for asking questions. You can raise your hand. I'll bring the microphone. Everything's possible. The next paper is going to be hashtag, and SIGCHI is here to present in behalf of Yanzhong Chen, who's the first author but couldn't make it. And I just want to pass the microphone to you and go for it.
Okay. Hello everyone. My name is SIGCHI, and I'm a PhD candidate from Stony Brook University. And today, on behalf of our team, I will give the presentation, the haptic compact actuators for rendering push-button tactilities on softer surfaces. So nowadays, the development of Internet of Things tends to outfit physical environments with digital abilities and also the experiences. And for instance, integrating sensing components to ordinary familiar objects like clothing or other daily life items, so which as a result afford a variety of touch and gesture interactions. So these novel interfaces usually involve actuations that mimic physical world interactions with input method like buttons, which are familiar interface components to users. But push buttons are essential UI elements, and we are used to seeing them in our daily life. Typically, push button consists of rigid components, as we already know before, and that are very hard to adapt to softer interfaces. But so there's a challenge how to convey haptic sensation of a push button on a soft and flexible surface like our clothes. So this has motivated the development of more compact, lightweight, soft, and even elastic actuators. So based on the previous work, we extend our contribution to surface haptics as well as soft and compact actuators. And surface haptics refers to the application of variable forces on a user's finger as it interacts with a surface such as a touchscreen. And majority of work explores electromagnetic actuators that create vibro tactile feedback in either normal or shear directions. And other tactile surfaces has been explored using the didactic materials and the mechanisms. The smart fluids, such as magnetorheological fluids, act as a mechanism that reacts to an external magnetic or electric field and change the material's stiffness. And also, shape-changing display represents another category of mechanism to enable physical visualization and tactile exploration to enrich the application in VR and AR domains. Okay, on the other hand, the development of embedded haptic interfaces and on-skin tactile devices has activated the need for soft and compact actuators. According to the previous research, soft actuators can be roughly divided into two categories in terms of actuation method. So one is directly activated by an external force, such as pneumatic or electromagnetic actuators. And the other uses the nature of the material itself through external stimuli, such as electroactive actuators. So combine these two types of actuators, the question is how to achieve a compact structure, soft and thin device without sacrificing the variability, and it can also provide a sufficient actuation force. This is a key research topic in the area of soft actuators. So in this work, we make a thin and compact actuator that can be attached to the softer surfaces and provide a strong force and also the displacement correlation for rendering push-button tactilities. So we designed our haptech based on the fundamental concept of hydraulic amplified electrostatic actuator, which achieved the zipping effect by applying a voltage that causes the charges to gather on both sides of the dielectric layer to produce an electrostatic force, and the force is theoretically derived from the Maxwell stress. Okay, so when there's no voltage is applied, the dielectric fluid fills the gap between the upper and lower dielectric layers and making them static at a certain angle. But when the voltage is on, the electrostatic pressure is generated there, where the liquid starts to be squeezed and transferred from the side to the center and raise a bubble to trigger the haptic sensation. So our haptech made targeted design improvements according to the interaction needs of the application scenarios. A haptech was constructed using a sandwich structure, and we have improved the dielectric layer materials and use a low cost and simple processing TPU as the dielectric layer. So in general, this work is our first step to discuss such types of actuators, advantages in establishing the haptic tags to support touch interactions on our daily life display scenarios. So this is a detailed fabrication process of our device. The first step is to make the cover layer, which is made by a mixture of PDMS and EcoFlex with a certain weight ratio. And the second step is to make the upper layer, which is the mainly functional part of the device. And it was composed of double dielectric elastomer layers coupled to compliant metallized PET film. And the third step is to use the same process to fabricate the lower layer, but only the direction is opposite. And the final step is to integrate the upper layer and the lower layer by heat sealing and inject the dielectric oil, fill the gap between the two layers as a motion amplifier, and finally attach the full sensor to sense whether the finger is pressed on the button or not to determine whether we need to switch the device on or keep it off. A haptech prototype consists of a high voltage power supply and a full sensor, as we already said in the previous slides. And actuator was driven using a high voltage power supply that can be programmed by Arduino to generate a user controllable voltage we can up to 5 kilovolt. And the activation of the high frequency switch can rapidly neutralize the voltage of the upper and lower electrodes, thereby forming a rapid depression haptic feeling due to the removal of the force. So these parameters can be used to design haptic patterns, including the timing, location, level, and also the duration of the tactile feedback generated. So this is a demonstration of our device. You can see the device can be actuated in different frequency. To verify our design aims, here we do two kinds of inline measurement to evaluate our device performance. The first one is displacement. The figure on the top can show the results of time and displacement curves and also the displacement change according to the voltage. Here we can see that the displacement will increase when the applied voltage increased, and it also shows a very good repeatability. And also the maximum our device can provide is beyond 500 micrometers, so which is far more beyond the human tactile threshold. And we also measure the force that our device can provide, and also as shown in the figure, the maximum force we can get is around 260 millinewton, and which is sufficient to trigger the human haptic sensation. And to stimulate the tactile feeling, here we design 3 typical push buttons. The first one is the linear button. This is the one when you press on it, you will feel like a spring, as the previous presenter said. And let's see the displacement and force curve. Both lie on the press and release phase is smooth without any huge amplitude jump. And the second one is the clicky button. So this type of button will provide a bump feeling, like when you press on a keyboard or you click the mouse. And on the displacement and force curve, we can see that there shows amplitude jump only on the press phase, but the release phase is still smooth. And the last one is called lock button. And this type of button will provide you twice bump feeling to make you feel that the button has been locked and unlocked. So as shown in the displacement and force curve, there is a huge amplitude jump on both press and release phase. So in this study, we only show these 3 kinds of proof of concept designs to stimulate the button feelings, use our haptic device. However, in the real world, the buttons are far more complex than what we have explored here. To evaluate the performance of our device here, we also have the user study about the perception of tactile response. So there's 12 participants have been involved in the evaluation. For each participant, we perform 3 series of tests. The first group is about 3 kinds of tactile response, as we already introduced in the previous slide. The linear button, clicky button, also the self-lock button. And second group is about 2 kinds of surface materials, the Noven, fabricate, and PDMS. We already tested, and this is a commonly used stretchable polymer. And the third group is 3 different interaction gestures, as shown on the slide, the touch, pinch, and inner. And for each participant, we repeat each single test 9 times to find out how well the users can preserve and distinguish the tactile response in stimulated scenarios and to evaluate the performance of the haptic. So there are the results of the user evaluation. As shown on the slides, we plot the confusion matrix of recognition. We also analyze the mean accuracy of the recognized the pattern when the users are under different interaction gestures and on different surface materials. The results show the mean accuracy of the device is beyond 93%, and the best combination is when the surface material is PDMS, and the users is under the pinching gesture, and when recognizing the linear button, And we also analyze the mean response time, which is lower than the 700 millisecond. So there are the potential applications. The haptic could be integrated in several haptic interaction scenarios. For example, clothes, waistband, and the plastic bag. And to trigger the haptic sensation underneath the leather or in the air. Okay, as we said in the beginning, this is our first step to explore in this area of soft haptic actuators. So in the future, we would like to contribute further in the following 4 aspects. The first is about the integrated pressure sensor. So in this work, we only use the sensing signal to be a switch to control whether it should be started or not. But in the future, we would like to involve more information provided by the pressure sensor to make the device a more compact structure with like a closed loop self-sensing system. So the second aim is to develop more force rendering. Now we design 3 kinds of typical push-button haptic patterns. But in the future work, we would like to develop more complex haptic patterns and like them to be more realistic. And third goal is about the compatibility. As we would like to integrate the haptic on a wide range of soft surfaces in our daily life. But in this work, we only try to embed the device on the nonwoven fabric. The last one is about the customizability. In the future, the users may have the ability to change the size or the shape or even stock several haptic units to meet the custom requirements. And in conclusion, this work we design and implement the haptic as a compact actuator to rendering the various haptic outputs, customize the cell-based designs, and validate of 3 push-button tactics with 3 use gestures on 2 kinds of soft surfaces, and we also embed it in our daily soft surfaces to enrich button based on interaction in abundant scenarios. So at the end, unfortunately, our team leader cannot be here by some reason, but here he brings a short lightning talk as a small advertisement.
Hi, I'm Yan Junchen. As the first author of this paper, I regret not attending WUST 2022. Now, I'm a research assistant at the Institute of Software, Chinese Academy of Sciences, where I'm advised by Professor Tan Han. I received my bachelor's degree in computer science in China. My research interest is haptic feedback and novel sensing, including compact actuators, sensors, and innovative wearables. I presented papers at SIGCHI, UBComp, and WUST. I'm looking for a PhD position in human-computer interaction. Hope to join your group.
Okay, so if any professor interested, yeah, and you can either contact with him or contact with me. Okay, so I'm very happy that you could listen to me at a very bad weather. Okay, thank you.
Any quick questions?
Hi, Alexandra. I'm Honey Melon. Super cool work. Thanks so much
Thank you.
for sharing that with us. I was wondering, could you make that kind of like in a pattern way, like make like full sheets where you have like buttons all over? What would be the limitations? I'm sure it's not easy, so I want to hear from the expert.
Yeah, it's really a cool question, and it's also what we want to research more in the future. So you can see we make this is like a unit. So you can like extend them into a pattern, but as you said, the control system will be much more complex. But it's also like a aim, and we already put some effort in it. Yeah.
Hi,
Yeah.
Quick Schultz, Carney Mellon. Alex took one of my questions, which is very, very good question. But thank you for the talk.
Thank you.
I was wondering a slightly adjacent question, which is, have you thought about kind of everything presented here is like one size of one module, larger or smaller for maybe different parts of the body? Have you
Yeah,
considered
yeah.
that?
Different parts of body is also what we already thought. And because you know the thresholds of the haptic sensation is different. So if we want to put on different parts, we need to like, it's also what we say the customers. And we now we want to be a very smaller because the finger is the almost the most sensitivity part of our body parts. So okay, yeah. So we already saw before for large one is easier than the smaller one. So but if we want to be much more smaller, yeah, there's a long way to go. But we already put some effort into like customize or be an array. Yeah. Thank you so much.
All right, awesome. Let's thank SIGCHI again for presenting the work. Welcome behind for the first author. All right, next up is the one and only Kentaro Yasu, who in my lab we refer to as Magnetic Sensei. He's really a pro in this stuff. And he's going to talk about magnet shape. This is work that he's done at NTT Corporation.
Yep, thank you for introduction. So, hello everyone. I'm Kentaro Yasu, a researcher at NTT Communication Science Laboratories. My paper is titled Magnet Shape, a non-electrical pin-based shape-changing display. So here we go. So let me start with the motivation for this research. So far, pin-based shape-changing displays have been achieved to present blade, undulating terrain, and actions of remote person to enable physical interactions. So I think these studies are so fascinating that anyone would like to try these kind of systems. However, especially for people without engineering backgrounds, the hurdles to purchasing, constructing, and operating such devices can be very high, as long as the actuation mechanisms are accomplished by electrical actuators. As the array sizes increases, construction of magnet shape. The video shows a prototype of magnetic pins. Each pin has a strong neodymium magnet at the bottom because I thought that the stronger the magnet, the higher the levitation height of the pin. However, if the magnets in the pins are too strong, their magnetic force will repel or attract the adjacent pins. This interference of magnetic forces makes the spatial pin resolution lower. This is a problem. So to address this problem, we use pot magnet. A pot magnet is made of permanent magnet and a metal pot. The pot, which is a container with high magnetic permeability, prevents the magnetic flux from leaking out and concentrates the magnetic flux on the bottom side. By using the pot magnets, the spatial resolution of the pin display was significantly improved. However, if the pot magnet is placed directly on the magnetic rubber sheet, the surface of the magnetic sheet will be immediately magnetized. So we performed a simple test to clarify the appropriate gap between the magnetic sheet and the pot magnet in order to prevent the remagnetization of the sheet by the magnetic pins. As a result, if a 1 millimeter gap is maintained between the magnetic sheet and the pot magnet, the magnetic pattern on the sheet will not be affected by the pot magnets. So we applied the 1 millimeter gap to the bottom of the pin array housing. Next is how to change the levitation height of the magnetic pins. As I showed earlier, the magnetic sheet can be easily magnetized with neodymium magnets. So therefore, by using this rotary magnetizing tool I made, we can change the stripe pitch of the magnetic stripes within seconds. By changing the stripe pitch of the magnetic patterns from 2 to 6 millimeters, the magnetic field distribution above the sheet will vary. Thus, the levitation height of the pins can be controlled by the pitch of the magnetic stripe. Besides, based on the measured values, we have implemented a pin motion simulator. It calculates the magnetic force between each pin and the magnetic stripes. This allows the user to see how the pin's behavior changes by changing the the pitch of the magnetic stripe, pin array size, pin pitch, and the relative angle between the pin array and the magnetic stripe. So we have also implemented a magnetic pattern generator. Simply input, generate, and send to the pattern, send the pattern to the plotting machine. The plotting head with the neodymium magnet will magnetize the right position on the magnetic sheet to present this kind of designed shape or characters. Furthermore, a simple animation can be displayed. By using a slightly shifted magnetic stripe, the timing of the maximum levitation height can be shifted. Thus, the pin array can display a circular ripple like this and a beating heart. Yes. Thank you so much. However, the port magnet I used cost about $13 per unit. That means a display with 100 pins costs about 1,300 $. That is almost the same price as the latest MacBook Pro. This is also a problem. So I devised two alternative and inexpensive fabrication methods of the magnetic pins. One approach is the pot-like method. By using small iron tube and washers, we made pot-like structures of different diameters and thicknesses. Then by inserting a neodymium magnet in it, we could create a pot magnet-like magnet. And the other approach is the punch sheet method. We create circular disks from magnetic sheets using a hole puncher and magnetize the centered periphery with opposite polarity to mimic the magnetic field distribution of the pot magnet. So though the user has to assemble and process some items, these methods significantly reduce the material costs of the magnetic pins. Then I created 23 types of magnetic pins in different sizes and measured the minimum pin pitch and the maximum levitation height of the pin to ensure the generalizability of our methods. As a result, there seems a trade-off between spatial resolution and the pin levitation height, but some of the alternative pins could present longer pin strokes and smaller pin pitch than the pin with the pot magnet. Moreover, the alternative magnetic pins are much lighter than the pin with the pot magnet. So when the magnetic sheet moves at an appropriate speed, the pins will achieve a momentary higher position than the maximum levitation height and the static conditions. So we measure the dynamic levitation height of the magnetic pins at different moving speeds. The result shows that both two alternative fabrication pins reached higher levitation heights than the pins made with the pot magnets. Based on the findings we revealed, we made several application examples. So firstly, it is easy to create, design, modify pin displays and motions. It can be used for education, storytelling, or simple kinetic prototyping. Secondly, the magnetic pins made with the alternative fabrication methods are good for visual use because they can levitate much higher than the pins made with the pot magnets. For example, by rotating the magnetic sheet by hand cranking system, it can present wavy motions endlessly. Thirdly, the magnetic pin made with the pot magnet is suitable for applications that use physical actions, such as moving a paper toy attached to the tip of the pin and ringing a bell or tapping a finger or palm as a haptic display. Now, here are the limitations and remaining challenges. The biggest limitation of this method is the short pin stroke and weak output force. With the pins with the pot magnets, the static levitation height is up to 4 millimeters, and the output force is less than 2 grams. The limitation can be improved by using pin made with alternative methods and thicker magnetic sheet. For example, when we used a 3 millimeter thick magnetic sheet, the levitation height was doubled in a static condition and nearly quadrupled in a dynamic condition. Alternatively, additional mechanisms or attachment might allow the display to present longer pin strokes and stronger forces. An extensional attachment or pin lock mechanisms might be helpful to present rigid forces. Another remaining challenge is interactivity. Although a slight modification can be quickly done with the magnetizer, though there seems to be room for developing a computational manipulation system to add further interactivity to the display. For example, MagneShape makes a small robot more expressive without wiring, soldering, or additional batteries. Alternatively, a robotic arm or a motorized XY table can be used to provide additional interactivity to the display. These interactive applications are the future work. That's it. Thank you so much.
Very good. I was joking when I said he's a magnetic sensei.
Thanks for your talk, Kentaro. I'm Vivian from Carnegie Mellon University. I saw that several points through your slides, like you showed the dynamically changing pin height, and also like when you change the width of the stripe, you can actually get it higher. I was wondering if you have any notion of like the static resolution you can get from different pin heights based on like offsetting the sheet of paper or sheet of magnet or something.
Yes. So, the levitation height can be changed by changing the pitch of the magnetic stripe, and if the magnetic pole is right beneath of the pins, it's the highest position. If it is slightly shifted, the pins will slightly downwards. So then changing the position of the polarity, so then the pin height can be a little bit controlled. Yeah.
Awesome. All right. Let's thank Kentaro once more. All right, we're moving on to Takeru's paper.
Oh.
All right, you're going to set up. Takeru Hashimoto is from the University of Tokyo. He's presenting work he did also with Shigeru Yoshida and Ikuji Narumi. This is a really cool device that I actually get the chance to talk to them at the demo.
Thanks.
And so I'm really excited to see this. Before we just switch, also I wanted to give an announcement from Kentaro's side. I forgot to say earlier, but he's looking for collaborators if you're interested in working with him on this beautiful magnetic stuff. So you should talk to him at the end of the session. All right, without further ado, let's hear about Metamorph X.
Hi, thanks for introduction. Hello everyone, I'm Takeru Hashimoto. I'm a PhD student from the University of Tokyo. I'm really happy to be able to talk to you today. Today I'd like to talk about our handheld torque presenting device called Metamorph X. First, here is an overview of our study. The goal of this study is to represent the haptic sensation of swinging or welding object of various inertia and viscosity using a single handheld device. We developed the ungrounded moment feedback device using gyro moment and represent these physical properties by moment feedback to the user's motion. So when we grasp and swing an object, we feel force through our hands. The force varies depending on the physical properties of the object and motion. So we try to represent these various physical properties in terms of moment feedback. So here's our motivation. So many handheld force feedback devices have been proposed in the field of SIGCHI or haptics. Some examples are shown in this slide, using propeller or gyro or air jet. Most of these studies use force feedback to represent dynamic components, such as pulling force or by summon or torque pulse torque pulse or impulsive force feedback. In this research, instead of such dynamic properties, we try to reproduce the static properties and objects such as inertia or viscosity. By doing so, we think we can extend the renderability of these handheld force-presenting device. So here's a principle. So based on the work of Tabe, that moment of inertia plays a dominant role in the perception of object properties, we focused on the user's rotational motion. So the equation here, or the equation of motion and the generated torque from the device by generating the moment proportional to the angular acceleration, as in the equation, and the moment of inertia is increased. Of course, the moment of inertia is not the only variable we can change. We also focused on the drag force that varies with angular velocity. By generating moment proportional to the angular velocity, the viscosity is increased. So here's a summary of our principle. In this study, we focused on the inertia and viscosity. By generating the torque proportional to the acceleration or velocity, we try to change inertia and viscosity of the handheld object. So next topic is how to generate force feedback. In this study, we focused on the mechanism called control moment gyroscopes that utilizing gyro moments to generate force feedback. The control moment gyroscopes have the advantage of low latency for force feedback around 60 milliseconds, and it can dynamically control torque over time. So we propose a torque output handheld device called Metamorph X to achieve impedance control in rotational motion. The structure of single control moment gyroscope is shown in this figure. There is a flywheel rotating at high speed and the gimbal motor that actuates a flywheel itself. So when the gimbal motor is actuated, like in this video, gyro moment is generated. By combining the movement of 4 control moment gyroscopes, the Metamorph X can generate 3 directional movements, as shown in this video. So now let's go into the technical evaluation. We evaluate whether Metamorph X can render torque proportional to angular acceleration and angular velocity. We use torque sensor to evaluate. Participants swung the device to the sounds of metronome, and we compare the value from the torque sensor and the desired value from the IMU. We evaluate the condition of swing frequency and swing direction, and the change of inertia or viscosity. For simplicity, we focused on the 2 Hz x-axis swing here. Please refer to our paper for more detail. So here's the result of additional inertia. In this condition, we try to render torque proportional to the angular acceleration. In this graph, the blue one is the angular acceleration, and the gray one is the desired moment, and the red one is actual torque by the torque sensor. The waveforms of the red one and gray one is really similar. So we can say that the generated torque is proportional to the angular acceleration, and the system can render additional inertia of 0.01. And the next, we show the result when viscosity is changed. In this condition, we try to render the torque proportional to angular velocity. From this graph, although the magnitude of raw moment differs slightly from the desired torque, but there is little disturbance in the torque output, and the waveforms of measured moment and desired moment is similar. So we can say that the generated torque is proportional to angular velocity, and the system can render additional viscosity of 0.1. Some of you may wonder if this device can render no force in user's motion. Here is the result of no additional inertia and viscosity. As we can see from the graph, the desired torque is equal to 0, and measured torque is also near 0. But there's a little torque disturbance, but compared to the moment generated from the original inertia of the device, it is about 10% in magnitude. So we can say that this device can somehow render no force. We also show the result when the additional inertia and viscosity is further larger. As shown in this graph, measured moment cannot track the desired moment, and sufficient magnitude of the torque is not generated. This is because the desired angular moment output for single swing has exceeded the allowable amount. So we found that additional inertia of 0.015 and additional viscosity of 0.15 cannot be rendered. Sorry. So here's the summary of the results. It is found that a moment of inertia difference of 0 to 0.01 kilogram meter squared can be expressed for each swing axis. This means that the moment of inertia changes about 2.5, 2.3, and 4.3 times from the original moment of inertia for each axis. The Weber fraction of the moment of inertia is about 14 to 22%, so human can sufficiently perceive the difference of the inertia that this device can render. And in the case in viscosity, it was found that the viscosity difference of 0 to 0.1 Newton meter second can be expressed for each axis. The Weber fraction of the viscosity about 30 to 100%, and the original viscosity of the device is really small, so the human can sufficiently perceive the difference of the viscosity. So finally, we created a VR demonstration, obtained user feedback through hands-on experience. In this demonstration, users were asked to hold a fan and fanning a fire in virtual environment. First, user will experience the different size of fan, where the inertia and viscosity changes depend on the size of the fan. Next, user experience the face of the fan burns. The viscosity becomes smaller and smaller, and finally, viscosity almost disappears, like that. So in this state, user cannot feel any drag force from this fan, broken fan, yeah. 9 users experienced the demonstration and were interviewed after the experience. We labeled and categorized their responses. We introduced some of the topics. The first topic is that the user mentioned more about changing in viscosity. In this demonstration, inertia and viscosity are increased at the same time, but users tend to pay more attention to the change in viscosity, where the ratio of change is larger than that of inertia. Since the original value of inertia is large, it may have been more difficult to users to feel the change in inertia compared to viscosity. So not only increasing inertia, but also decreasing inertia by torque feedback can make it easier for the users to feel the change in inertia. That's our future study. And 2 participants also reported that the force is felt differently depending on the direction of the motion. The equivalent 4 control moment gyroscopes are arranged to provide equal force output in the 3 axial directions. But these findings indicate the placement of the control moment gyroscopes can be optimized for human torque resolution and sensitivity for more efficient renderability. Lastly, we show the summary of the study and finish this presentation. Thanks for paying attention to our presentation.
Awesome. Any questions, raise your hand. There we go. I'm going to go over there. I'll bring the microphone to you. Don't worry.
Yeah, thank you for a great talk. I'm Ken, actually from the same university. Well, you said that the latency was about 50 milliseconds. And I was interested about how the users felt about that latency.
In the demonstration, the user not mentioned about the latency. Maybe some of you come to our demonstration 2 days ago. Later participant mentioned about the latency.
Interesting, thank you.
See one more final question, and then we're going to close the session.
Hi, thank you for the fascinating presentation. I'm Alex from Arizona State University. How did you select the mass of the wheel that you used? Are they an off-the-shelf component, or did you specifically choose the mass to enable a certain force feedback?
So the question is about
the weight of the wheels that you use.
Yeah, the form factor of this device is about weight, so that we choose the whole device is under 1 kilogram. It's okay?
Takero, I think
yeah.
the question is about the flywheel. And I remember you mentioning in the demo when we were talking that you had 3D printed the flywheel.
Oh, yes,
right?
yes. Yeah, that's 3D printed. And it weighs 30 grams also.
Awesome. All right, just a final announcement. I know we ran a little bit over time, but this was such a cool session. All these people are here, right? So you come talk to them, ask more questions. I also want to mention to the PhD students in the room, sorry, the prospective PhD students in the room who are interested in finding more about how to work with these people that, you know, Michael Haller is hiring postdocs and PhDs, Alexandra Ion as well. Kentaro is looking for collaborators for the magnetic adventures. So just come talk to these people, and don't forget to vote on those best talks. If there was something that you liked here, not only this is a lot of work to put these amazing talks together, but reward them, you know, take the photo of that QR code and go vote for them. Yeah, thank you so much for joining me in this session. It was a pleasure.
horizontal or vertical visual references for the next tasks. Users were asked to do 4 space perception tasks: line, distance, direction, and position. Each task was repeated 30 times. Line perception task is where the user adjusts lines of random angles and positions into horizontal or vertical lines according to the voice prompts. Due to the virtual scene doesn't have intuitive horizontal and vertical visual references, users need to rely on the perceptive information from multi-senses. Distance perception task is where the user observes a first sphere at a distance of 3 meters and a random position for 5 seconds, and then adjusts a second sphere at a random distance of 2.5 meters to 3.5 meters to be the same distance from the user as the first sphere was. Direction perception task is where the user points at the center of a target sphere at a random position and distance with a 0.5 meter long ray. Position perception task is where the user aligns the center of a white sphere on the handle with the center of the target green sphere. The two spheres are different sizes and the green sphere is rendered to occlude everything, for preventing participants from simply relying on the visual occlusion relationship. The results showed that upright redirection increases spatial perception divisions of horizontal and vertical lines, the distance of objects, the directions of objects, and the perceptions of objects, as the physical body's sensory information such as gravity, body orientation, etc. interferes with the space perception of the upright VR environment. Moreover, compared to no head turn, the skewed problem of turning head at the reclining and laying positions leads to bigger perception divisions for the left object and the right object. Interestingly, Study 1 and 2 showed similar results between conditions. That is, 45-degree reclining position was most affected by upright redirection rather than 90-degree laying position, which had the biggest redirection angle. Based on previous series, we speculated on the reason for this result. At 0-degree sitting position, all senses matched, resulting in the best internal and external perceptions. On the one hand, as the body tilt angle increases, the upright redirection angle increases, and so does the degree of sensory dissociation, which leads to worse perceptions. On the other hand, increasing body tilt angle also lowers the sensitivity and weight of the vestibular system. This means that the vestibular system plays a less important role in the multisensory integration process, thereby reducing the sensory conflict and its impact. The combined effect of these two aspects made the 45 reclining position have the biggest sensory conflict and the worst perceptions, and made the 90 laying position have the small sensory conflict and the good perceptions. As evidenced by the previous literature, 90-degree laying position reduced the motion sickness and was more easily confused in the body orientation perception than in other postures, due to the reduced sensitivity and weight of vestibular system. In Study 3, we designed 4 interaction techniques to strengthen upright redirection in VR. These methods were categorized as illusion-based methods and sensory-based methods. Instead of presetting users with upright redirected views directly, we proposed dynamic upright redirection to let users experience the tilting process. For example, when a user needed to conduct an experiment in 45-degree reclining position, the experimenter first adjusted the chair back to a larger angle such as 75 degrees. When the user entered VR, the initial view and avatar was also tilted. The experimenter manually rotated the chair up by 30 degrees, while the avatar and view are dynamically rotated by 2.5 times the rotation speed of user's physical body. Based on the fact that the vestibular system can't distinguish between static and uniform linear motion, we gave up some motion realism and substituted the original variable speed motion with a uniform linear motion at the original design's average speed, 1.5 meters per second, to reduce the sensory conflict. The users felt support force on the back and friction on the head when turning their heads. This was not like an upright feeling.
To mitigate such the proprioception vision conflict, we got inspired by the airman and the rocketeer from the game Red Alert. A virtual jetpack was rendered behind the avatar to visually match the body support force and head turning friction force when the avatar was standing or in motion. To solve the skewed problem of turning head in a reclining or lying position will involuntarily turn into an arc, we proposed head turning redirection algorithm based on users' head orientation data in the physical upright positions and the reclining positions to real-time calibrate the skewed views into upright views. We used a combination of pairwise method for evolution rather than 4 methods separately, so 4 conditions were set up in this study. We chose the 45 degree with the worst perceptions as the experimental reclining angle. The tasks were the same as study 1 and 2 with simplifications, but reduced their task times and repetitions. We were pleased to find that the interaction method played a certain effect in improving self and space perceptions of upright redirection. The condition with both illusion-based and sensory-based methods resulted in the best internal and external perceptions. We speculated that this was due to when in the strong upright illusion, the width of matched vision and proprioception that supported the body was upright became higher, and the weight of vestibular sense was further reduced. This resulted in less interference and misleading of the space perception caused by the reference frame based on the physical body's gravity and orientation. Overall, these findings proved again that relative reliability and multisensory weights seemed to can be changed by manipulating the vision contents. Finally, our studies have some limitations. First, the analysis and inferences of the results of study 1 and 2 are based on the experimental results and past series. We don't rule out that there are other factors that might play certain roles in the process. In the future, we need to find more evidence in the neuroscience field through more experiments to make the inferences better evidenced. Second, the interaction methods in Study 3 are preliminary explorations based on previous series and findings. They have some limitations and are not necessarily optimal solutions. For example, lack of testing of each method independently and investigating of other reclining or lying angles than 45 degrees, etc. Although upright redirection does cause extrasensory conflict, we believe that a comfortable reclining and lying position is a good choice for lazy people, passengers, long-term immersion people, patients in bed, etc. We hope that the findings can help researchers to better understand the upright illusion and its perception principles, inspire novel interface design, and provide a new perspective for the popularization of VR in reclining and lying positions. Thank you for your time. If you have any question or want to know more details, please contact us or refer to the full paper.
Tsinghua University, so he presents color to depth mapping the depth cues in virtual reality. So his also write, 一kan kui tianzhen shou yu jian yun tao wang yu kan yang Michael Nebelin and Yuan Chun Xi from Tsinghua University, Carnegie Mellon University, and University of Michigan. So stage is yours.
Thanks for introduction. Hi everyone, I'm Zhipeng Li from which one is what? Hi. Okay. Hi everyone. I'm Zhipeng Li from Tsinghua University. I'm now a PhD candidate, and I'm excited to present our work titled "Cultural Depth Mapping and Depth Cues in Virtual Reality." This work is a collaboration with researchers from Tsinghua University, CMU HDI, and University of Michigan. And Yukang Yan is the corresponding author of this paper. He is my mentor in this project, and we work closely through the whole project. Okay, thanks. Okay, so first here is a demo of our cultural depth mapping. We color the sketch to reflect its depth. The stroke becomes black when it is further from the user and becomes white when it is closer. Therefore, the user can perceive the depth better and sketch a 3D object more precisely. In this talk, I will show you how we use the color as a depth cue in virtual reality to improve the user's depth perception. So depth misperception in VR has been a consistent issue. For example, in this figure, it is hard to tell that the sculpture and the spheres, which one is closer and which one is further. Well, VR enables some supplemental depth cues by rendering the object of different depths differently to mediate the lack of depth cues. Like, for example, using color or blurriness or opacity to provide extra cues. However, these depth cues are defined by designers based on their experience, and users need to memorize them. So we would like to investigate how users perceptually map a certain attribute to depth to provide more intuitive and effective attribute to depth mappings. To this end, we choose color as an example attribute for investigation. So here is what we do in this paper. We investigate how users intuitively map the color space to depth. Then we construct a computational model to generate color to depth mappings. And then we evaluate the generated mappings and demonstrate its benefits with multiple applications. So before we go to details, let me define what is a color to depth mapping. As the figure shows, a color to depth mapping contains multiple pairs of color and depth. So in each pair, users will map the color to the depth and then retrieve the depth from the color. So how to get this mapping? We first understand how users map the color space to depth. Although RGB is one of the most well-known color model, well, HSV is perceptually meaningful, so we use HSV color space to characterize a color. We investigate how users map these channels to depth. We design a task to ask the users to map a color to depth. We render a trail square with a given color and put two references to rule the moving range. So users are instructed to put the trail square at a depth between the two references where they find the target color reflect the depth most intuitively. So we first investigate how users map a single channel to depth, and we start from hue. The independent factor is hue, and the control factors are saturation value. The dependent factor is the depth that users map the color to the color, map color to the depth. After collecting 16 users' data, the left figure plots the average and the standard deviation of the depth that users map to. As you can see, every color's average depth is similar with others, and like the right figure shows, users map the hue to depth in a reverse manner. This indicates that there may not exist a consistent hue to depth mapping. So let's talk about the saturation. With a similar study design procedure, we collected another 24 users' data on 6 hues. So the position of each color bar is the average map depth, and the length is the standard deviation. The results show that users can map the saturation to depth in a consistent manner. And as you can see, users can map the saturation to about 3 or 4 different depth levels. So what about the value? With a similar study design, the results show that users can also map the value to depth consistently, and participants can also map this value to 3 or 4 different depth levels. So compared to hue, participants achieved more consistent mappings with saturation value. So the next thing is we're curious about what will happen if we map the saturation value to the depth simultaneously. Will there be more depth levels if we consider saturation and value at the same time? And will there be any interaction effect between the saturation and the value? So with these questions, we conduct another joint study. We alter the saturation and value at the same time. The results show that participants can map the saturation value space to more depth levels, and there is an interaction effect between the saturation and the value, which indicates that we must consider saturation and value at the same time. So after understanding how users map the color space to depth, we then implement a computational model to generate color to depth mappings based on the previous collected data. So with the previous study results, we found that users map the same color to a depth range. And if two colors' depth range overlap with each other, users might be confused when we use them to indicate the depth. So if we would like to reduce the confusion probability, we can use less color in the mapping to ensure that every neighboring color's depth range doesn't overlap with each other. Like in this figure, we can only use the white and the black. Obviously, such a mapping is not practical. So if we want more depth levels in a mapping, there is more likely that users will be confused. So we would like to generate a color to depth mapping that contains the most depth levels at the same time satisfies a confusion probability requirement. To do this, we constructed a computational model based on the previous data. Since we have each color's depth average and the standard deviation, we use a normal distribution to model its depth range. Based on that, we can calculate the overlapped area between any two colors, which represents the confusion probability. With this, we implement a model that takes in the confusion probability requirement and outputs a color to depth mapping under certain constraints. Like the figure shows, if we would like a mapping whose confusion probability between any two colors is less than a certain value, it turns out to be a longest path in the map, which is a mapping that includes as much as possible depth levels and it satisfies the requirement. Then we conducted an evaluation study to show how our generated mapping improved users' depth perception in VR. We choose mid-air sketching as our task since it needs the user to draw spatially precise, which is hard due to the depth misperception in VR. Users are instructed to follow the target shape and draw a similar shape on the other side. We designed a factorial study. The first independent factor is whether we use the color to augment the target. If the target is colored, users can perceive the target's spatial structure better and thus might be able to draw a more precisely sketch. The second one is whether we color the user's sketch. If the sketch is colored, the user can know whether he's drawing in the right way or if any adjustment is needed. And the last factor is whether the shape is 2D or 3D. 3D shapes are more spatial complicated, so we would like to know if our mapping can improve the performance on both of them. For the objective results, we mainly focus on the similarity and depth error and the computation time. The similarity error is the shape difference between the target and the sketch, and the depth error is the depth difference. The results show that on 3D shapes, if we only color the target or the sketch, the similarity and depth error can be significantly reduced. However, on 2D shapes, only when we color the target and sketch at the same time, the error can be reduced. And meanwhile, the computation time is not significantly influenced by the color to depth mapping. This indicates that users can draw better without using more time with our mapping. And as for the subjective results, we would like to know if users find it easy to use or feel confident with it or feel mentally tired with it. On both 2D and 3D shapes, users feel easier and more confident only when we both colored both the target and the sketch. It is because users can refer to the target and know if their sketch is accurate or not by perceiving the color. Meanwhile, users do not feel more mentally tired when the color to depth mapping. This indicates that users do not need to pay extra effort to perceive the color and think about the depth. They can perceive the depth from the color indirectly. So users can, both the objective and subjective results show that our color to depth mapping can improve the mid-air sketching's performance and experience. So let's move on to the application part. To further demonstrate our mapping's benefits, we developed 4 different applications. The first one is about the gesture. To get the user to perform mid-air gestures in VR, we color the gesture guiding with our mapping so that it becomes easier to perform spatially complicated gestures. And in a virtual interface layout arrangement demonstration, we color the UI elements to cue their depths, which allows users to precisely different virtual elements at different depths for interaction purpose. In the 3D data visualization, we color the data points to refer to their depths dynamically as the user's viewpoint changes. As you can see, the closest data point will be white, while the further one is in pure color. In this way, users can perceive the 3D data better. We also extend our technique to the real world by augmenting physical objects like the cars or the walls in a parking lot. Therefore, it is easy for users to know the distance to these objects, and users can prevent to collide with them. And next is about the discussion and future work. Even for the color, there are multiple different color models like RGB or CDIE, and other visual channels may face different scenarios better than color, and it is worth to explore these channels in the future. And to use the color to depth mapping in our daily usage, there might need some additional support. For example, when the environment color could be essential for the user, like the traffic lights, to solve these issues, we could apply a mode switch in our practical use. We could also show our color augmentation and the objects original color simultaneously, like we can add in some colored outline around the object. And it is also an important future work to implement personalized color-to-depth mapping to provide more depth levels with less confusion probability. So here are the takeaway notes. In this paper, we conclude that situational value can intuitively cue depth in VR, and we present a computational model to generate intuitive color-to-depth mappings. With an evaluation study, we prove that the mapping can improve the mid-air sketch performance and its potential to benefit multiple applications. So for more information, please refer to our paper. Thanks for listening.
From Columbia University. I think it's really important to do the work that you're doing in trying to understand better ways of being able to convey depth. But one thing I was curious about, there is a fairly well-known concept called chromostereopsis that's usually attributed to chromatic aberration in the eyes, in which for many people, but not all, red things appear to be closer than blue things. And I was just curious, I didn't see any mention of that or any attempt to try to study that in comparison with the other coding approaches you used.
Thanks for your question. Like in the depth image, like captured by the depth camera, we often use red to represent the closer things and blue in the further things. That is designed by designers. So in our Q to depth study, we found that users can map different color for different hue for the closer things and different hue for the further things, and as you may know, the hue is in a circular form, so users may like map the hue to depth in different order. So like it is hard to use different hue to represent the color. So we use saturation value. So and it is possible to like combine different hue. Like we can use like start from white and then to red and then like to black and then to blue and other hues to provide more depth levels in the mapping. So, yeah.
Because I mean, chromostereopsis is a physical phenomenon based on how things focus and where they focus. It's not just an arbitrary decision that red is close and blue is far away, even though it doesn't work for everybody.
Yeah.
Yeah, but I was just surprised that you didn't actually include that as one of the things you studied.
Yeah. Okay. Thanks for your question.
Thanks for the nice talk. I'm John Kim from Korea. So is there any interaction effect between the hue and your method? For example, different hue and different effect on the depth perception with your method?
I'm sorry?
Is there any interaction effect between the hue and your method?
Actually, we didn't like investigate the hue and other channels simultaneously, so it is hard to say if there is an interaction effect. But I think there is. Like, for some hue, users can be more sensitive, but for some hue, they may not. So, like, it is interesting future work. Yeah. Thanks.
All right. Thanks, speaker again. Okay, so the next speaker is Jonathan Sutton. So he's presenting look over there, investigating saliency modulation for visual guidance and with augmented reality glasses. So this is the co-author by Tobias Langkopf, Alexander Plovsky, Stephanie Zollman, Yuta Ito, Holger Logenstadt from University of Otago, University of Tokyo, and Graz University of Technology. So, thank you.
Working? All right. Hi, I'm Jonathan from University of Tokyo, and today it's my privilege to present to you our research, Look Over There, investigating saliency modulation for visual guidance with augmented reality glasses. So, as said, this was a collaboration between myself, Tobias, Alexander, Stephanie, Yuta, and Holger. And so the idea here is if we take a scene on the left and you're just looking around in AR, a common application is that we might want to direct your attention to somewhere in the scene. And so traditionally in AR, this has been done using graphical overlays, say introducing arrows or outlining objects, such as the circle there, And this has been shown to work. It's used quite commonly, but there are also considerations around it with things like occluding the scene that you're looking at, being detrimenting the context and how much you can actually understand the scene you're seeing, as well as if you're already in an AR scene, you're introducing extra clutter and things into the environment. And so we wanted to look at going down a different route where we look at more naturally interacting with your view of the world and being able to actually adjust how you're seeing it to draw the attention in a more natural way that avoids these issues. And so we specifically looked at using saliency, or what draws your attention in the environment, and adjusting that to draw your attention. And based on previous literature and doing this on screens and HMDs, we particularly wanted to look at doing this in a more subtle manner. And so as I say, previous work has looked at how to direct your attention and adjust where you're looking in images and image material. So starting in psychology, but also in computing, it's been quite commonly done to adjust images and videos. This is normally done offline and in slow processes, but there have been some works that have looked into mixed reality and have actually demonstrated doing this in real time and adjusting your view. However, we want to look into doing this in AR glasses, and we believe the optical see-through head-mounted displays being the more preeminent system devices being used for this. We wanted to use these, and the previous works don't directly translate through to them for various reasons. For example, in optical see-through head-mounted displays, we are limited in the amount of light that we can control. In image material, we have direct control over what we're seeing, but with optical see-through head-mounted displays, we have to actually consider the real world. And for most common architectures, this means that we have only additive displays and can only add light into the scene. So this is an example of a prior method that would normally both increase and decrease the light. So that would be on the left there, and the center is if it was only additive, and then on the right, we have the, we're just showing the mappings of where it's actually adding and subtracting from it, with the red being the additive components. So in this research, we can contribute an overall explanation of saliency modulation in optical see-through head-mounted displays, where we developed a modulation that works with the current architecture and considers the constraints of them. We implemented it into several lab prototypes, and then we ran some user studies to investigate if it was feasible and its efficacy. So how this all works, if we take this scene here and we consider that we have someone wearing AR glasses looking at it, and we pick out a random point in it that we want to direct their attention to, so in this case just these flowers here, and if we predict a gaze map on that, well, we'll see that we don't actually expect them to be able to look, or we don't expect them to readily look there. So what we want to do is adjust the view of that scene such that we do expect them to look there. How we achieve this is we add to the optical see-through head-mounted displays a pair of beam splitters in front of their eyes that redirects light that they're seeing into the cameras. This gives us a view of the scene that's virtually on axis with their eyes. Taking that view, we can then calculate or produce an overlay mask to be displayed on the HMD. For us, this mask is how we modulate the saliency. For us, this means adjusting the contrast, the saturation, and also to do pseudo focus effects. We look at blurring and sharpening. So if we combine that with the scene, we adjust the view of it and produce that desired effect. So we created various prototypes to do this, starting with the bench prototypes. The advantage of these, we mainly worked with the bench prototype for our user studies, is that it gives us a very controlled environment. Working with users in the user studies on the other prototypes, or in the constrained stereo prototype, you very quickly have problems with not knowing how well they've calibrated eye display calibrations, and when you want to have precise modulated overlays interacting with the real world, this becomes problematic. So we work on the bench prototypes initially. There is also another reason behind this, and that was whilst we did integrate eye tracking into our other prototypes, we found that it was particularly unstable, and if you take other optical see-through head-mounted displays where you are able to have good integrated eye tracking into them, they then introduce other problems such as problematic with modifying them, as well as if you've used the HoloLens 2, you know that there can be color aberration issues, particularly if users don't look directly through the display and have it tilted or slightly off angle. As I mentioned, we did also create a stereoscopic prototype in which users were able to look through the system and directly have the vision modulated, and we added a chin rest and a head strapping to it, so we had their heads constrained to it. And then just for more demonstrative purposes, to show that we can move away from these big constrained prototypes that we were running, we've built various demonstrative prototypes, but I won't go further into them. So this is a bit of an exaggerated version, just showing what it might look like moving through our system. So that's just moving a GoPro down and to look through the system and show how it's adjusting the view of the world. Just quickly before I move on to studies, we did, based on the previous work, we ran a set of an initial study to set the parameters for our algorithm such that we thought we would be able to produce this subtle modulation effect, and I will leave you to read the paper if you want further details on that. So to say, we ran an initial study to look at the efficacy of our system. Using the bench prototype, we streamed the view through it into a head-mounted display, particularly in ViVi Pro, so that we had stable eye tracking. We could control the environment the users were seeing, and they could just look around freely, but we maintained the position of the screen in front of them so that they were always looking at the content. And we looked to consider 3 different conditions. So these have the gaze maps of someone looking at that image on them, and we looked at the unmodulated conditions, so if they were just looking at that image. If we then modulated it with a target area in mind, as well as we also wanted to see how our process compared to using geometrical approaches, particularly in how much they actually explored the images. Just to come to our results from the study, if we look at these images on the top right, starting from the left, we have the original image shown to them. And then from the next in red, we have a heat map showing the average gaze distribution across all participants for that image in the unmodulated condition. In blue, we show where the gaze distribution was for modulated condition, and then in the green, we show the effect for the circles, or the geometric outlines. Overall, we're able to show an increased number of fixations on the target areas, reduced time to fixation. We increased the area of the image they explored relative to the geometric effects. Although one thing I didn't mention is we also asked some questions just very generically about how they perceive the images to see if they actually perceive them differently in the modulated and unmodulated condition, and we did have a significant impact there. There's quite a few different graphs and stats there. Look in the paper if you want to know the details on them, but we ran the stats in various ways based on previous literature to see if we were having an effect. So after that, we did look to see if this translated through to our direct see-through prototype. We did have to throw away most of our participants, so we ended up only collecting 8 out of 15, I think we ended up using. And for this study, we only looked at whether or not the increased fixations and the time to fixation. We didn't ask questions or look at the other condition because we were looking to try and maintain as stable eye tracking as possible, and so that we could actually get some results out of it. Overall, in this, we did again show the increased fixations, but only for one of our tests do we actually show an increased time to first fixation. And in the paper, we do discuss why we think this might be and some reasons behind it. So overall, we investigated using additive saliency modulation, which we implemented in optical see-through head-mounted displays and then verified it via our user studies. There's various areas of limitations and future work, and some things were that we did have a noticeable impact on the images, as well as we found that the parameter space is very complex, and we did everything with just generic parameters across all our scenes, which shows up in the results, and therefore exploring parameters for scene-dependent parameters would be a future direction. But overall, we provided an alternative approach. We show an alternative approach to visual guidance in augmented reality glasses. So with that, I'd like to thank you for your time and point out that we do currently have funded PhD positions on other AR projects and interesting projects for students down in New Zealand.
Thank you, Jonathan. So if you have any questions, yeah. Hi, Jonathan. Super cool work. So you perform these modulations on the image on a low level, or to change the color of the graphs, for example. However, what you're simultaneously modifying are some higher level information, like plausibility. Why is this graph blue? Did you see any effects that higher level, kind of, if you change something on the high level of information of the scene, that those attracted more attention? Or did you do some analysis of that?
So we didn't do analysis on that. We wouldn't change the actual color of it. The colors is pushing it towards, say, a gray, a desaturated, or a, but yeah, you would have that effect, I guess, at higher levels. No, we didn't do analysis, and we didn't really see anything in the results that would suggest it, but it would be something to look into, to be honest.
Okay, thanks.
Hi, Johnson. It's me, Chinjang from Keio University. I personally inspired by you and Tobias and Yuta a lot. So my question is apparently out of your current scope. It's like I realize all the modulated pictures are somehow bottom up, right? So have you ever considered how to overcome those top-down CDS modulation, for example, how to like reduce some face-heavy object CDNC?
So you're asking about the fact that we just focused on a bottom-up saliency and didn't consider the top-down? Right, yes, that's one thing throughout the study and through our research is that we were focusing on bottom-up saliency, so what's really in the scene and not where a user's attention is, what task they're trying to perform. In fact, for our studies, we deliberately tried to avoid having a specific task for them. We just asked them to look around the images and then rate them using our questions afterwards to try and avoid that effect. So it's an interesting piece of research to do going forward is how this would move into where people actually have a task, whether they're looking for something, trying to maintain attention on something, or just having emotion in the scene, people in the scene, other things like that. Yeah.
Thank you very much. Very good work. Thank you very much.
All right, thank the speaker again. So the last talk is also the remote, so he couldn't come. So I gonna show the pre-recorded video. Okay. All right, so the last talk is VR Hook, a data collection tool for VR motion sickness research. So this, so Elliot Wen, he's not coming today, so he will present with pre-recorded video, but he's co-authored by Tandu Kaduchi, Shamane Sriwandana, Vanessa Tang, Mark Billinghurst, Robert Lindemann, Richard Yao, James Lin, Suran Nanayakana from University of Auckland, University of Canterbury, Facebook, and National University of Singapore. So he will be answering the question over the Zoom after that, but let me just play the video. Sorry, wait a minute.
Hi everyone, I'm Elliot. I'm very happy to share our research with you. The title is VR Hook, a data collection tool for VR motion sickness research. VR gaming has been gaining widespread popularity in recent years. However, according to previous research, up to 40% of users still suffer from VR motion sickness. The eye fatigue, nausea, and disorientations are among the most common symptoms. They can negatively impact the VR user experience. Many research results suggest that VR content is the most influential factor for VR sickness. Potential factors include fast-moving speed, excessive rotation, wide field of view, and inappropriate depth of view. Recently, researchers have attempted machine learning approaches to identify the presence of motion sickness content factors in VR games. Despite the progress made, many of these studies point out that their models are constrained by the size of training dataset. To improve the model generalization, we need to acquire larger datasets containing many thousands of video clips of VR gameplay and the corresponding risk factors. Unfortunately, conventional data acquisition strategy cannot meet this requirement. Firstly, manual annotation by human expert is very expensive and does not scale with the number of games. Secondly, building custom-made VR games for data collections wouldn't generalize the generalizability issue. Finally, modify existing VR games to extract the data would require some source code access, which is practically impossible due to the proprietary natures of most VR games. To overcome these challenges, we present a novel data collection tool named VRHook. VRHook can automatically extract labeled data from a wide range of real-world VR games without accessing their source codes. A core mechanism for our tool is dynamic hooking, where we inject custom codes into runtime memory to intercept low-level graphic pipeline data. In particular, we are interested in video frames and transform metrics, which can be used to extract video clips and many useful ground truth labels. Here's a quick demo of our tool.
To use our tool, we start our VR game as usual. Afterward, start our capturing tool. The tool will automatically locate the gaming process and intercept useful data from it. The data include iBuffer frames, 3D scene translation, rotation, headset and joystick movement, luminance, field of view, depth information, etc.
Our tool intercepts data in two levels. The first one is GPU level interception. We place hook on low-level graphic API stacks, including DirectX and OpenVR. They are highly standardized and remain almost the same regardless of the games being run and machine being used. As a result, our tool can place hooks on almost the same memory addresses in this stack to extract data from many real-world VR games. To acquire the transformation metrics, our tools can intercept constant buffer submitted to vertex shader. To obtain the video frame, our tools can intercept the swap chance to obtain the back buffer. The second level is engine level interception. The idea is that almost every VR game is built atop Unity and Unreal Engine. These engines have very standard internal rendering pipeline where we can place hooking function. Compared with the GPU level interceptions, this allows us to capture more semantic data, such as object names and light source location, etc. VRHook can capture two types of data. The first one is VR scene data, which is automatic data. It includes RGB images, camera setting, object data, depth buffer, optical flow, and user joystick input. In addition, our tools can also capture use self-report. And we achieve this by displaying an in-game slider overlay on any VR game. This allows us to incorporate a previously validated dial mechanism to collect self-reported comfort score from users. To show the utility of VRHook, we built a proof of concept machine learning pipeline. Given a gameplay video, we feed it into a slow-fast model to detect the presence of factors that might contribute more to motion sickness, and these factors are further fed into a support vector machine to predict the comfort score. Our results show that the pipeline achieves decent performance, and the performance can be further improved by feeding more training data and do some parameter fine-tuning. Recently, we are collecting more data from all of the show VR games from different genres. We aim to make a dataset contribution which is similar to ImageNet, but in the context of VR motion sickness research. If you are interested in this dataset, you can contact us at this email to acquire the dataset. Thanks for your time. I'm happy to answer any questions.
All right, thanks, Elliot. Thank you for the presentation. So he's over the Zoom, so if you have any question, please raise a hand or come to the mic.
Professor Suzuki, I can't hear you. Sorry about that.
You can hear me? Wait a minute. Can you hear me now? Okay, cool. Any questions? Okay, then yeah, I can probably, yeah.
Hi, this is Bala from Microsoft Research. I was curious how you were using the depth maps to understand motion sickness in the scene. Like, what's the core
Sorry, I can only catch you partially. Suzuki, would you mind repeating the questions?
So the correlation between depth map and motion sickness?
Because we are using the machine learning approach, so it's sort of like a black box. So because it's a machine learning approach, it's a black box approach. So what we do is that we just feed the depth map into the models, and the label will be the motion sickness scores. So we wouldn't quite know the internal mechanism how depth maps will cause motion sickness. It's just because of the machine learning natures, the black box nature. Yep.
Cool. Yeah, in case no one's asking other questions, I have one follow-up. Is there any specific intuition in which you are better featurizing those depth maps, or is the idea that depth maps are one of the easier ways to capture the 3D data in the scene? Basically, in short, are you featurizing the depth maps, or are you feeding them as direct images?
I see. So far our machine learning pipeline is still quite preliminary. The input of our machine learning pipeline is just the RGB image and depth image, and we have our machine learning pipeline has 2 layers. The first layer just output some well-known risk factor, for example, whether the thing is moving, the camera is moving too fast, or the camera is rotating too fast, or the camera is accelerating too fast. And based on these three well-known factors, we further feed into support vector machines to predict the user scores. So as I say, we didn't use our machine learning pipeline just a proof of concepts. So we didn't use too complicated machine learning pipeline. It's definitely a future direction to look into.
Cool. Thank you so much. So thanks, Elliot, and thanks all the presenters again. So thanks so much. All right, so this concludes XR perception session, and then we are having the vision talk here shortly in 3 minutes. So stay tuned and just keep sitting. And again, thank you for the presenter, and thank you for coming.
There's a normal. Good. Hi. Yeah. Well, I can, if you want to give it. Well, let's try this one, make sure it works.
Are you good with recording and streaming this session, or are you good with recording and streaming this session?
With it streaming,
Recording and streaming.
Recording, yeah, that's fine. Yeah, thank you. All right. Oops. Unless my computer decided to seize up, which is, can happen. Actually.
It especially likes to happen when it's
when you're. Let's see if that helps. All right, I'm going to do a hard reboot because. Yeah. I won't have the dongle plugged into. Let's make sure it works before we give it back to her.
Do you want me to grab you a glass of water?
It made noise. Yes, I don't. Jake sent me this front slide. I have no need to have my picture projected on the. But that is, if we want to.
You can take it off.
I'll just do this then. I guess I should plug in first. Oops, and I don't want my Teams being projected. This is actually quite confidential, so.
Okay.
Okay. The other thing I'd like to get is this presenter notes. Yep, and that shows up, which is great. So we can, I'll give this to Harmon.
Okay, hi everyone. Please take your seats. We're about to get started. So, welcome to our second Visions talk, our last one. Thank you all for sticking around and watching. This will be great. It's my pleasure to introduce Jamie Teven from Microsoft. I've known Jamie since the year we both graduated college. In that time, I've become old and Jamie's become distinguished. She is Chief Scientist and Technical Fellow at Microsoft, leading efforts on the future of work, and I think we'll hear about some of that today. Before that role, Jamie also was a technical advisor to Microsoft's CEO, which is really fancy and exciting. And before that, you probably know her from her long time at Microsoft Research. And most of you probably know her from her work on HCI, but she is equally famous also in the information retrieval community and has done a lot of really exciting work, everything from microtasks to re-retrieval and searching and so on. So for all this work, Jamie's received many awards, including the MIT TR35 and the Karen Spark-Jones Award, which is given to people in information retrieval. It's very fancy. Jamie spends a lot of time thinking about the future and how we can shape it, and so we're very excited to have her here presenting for this Visions talk. So let's welcome Jamie.
Thanks, Eitan, and thanks all of you for being here. It's fun to get to expound a little bit on the future, and it's particularly fun to get to do that in person right now with you. You know, I'm not constrained by a little box. I can move around, although I think with the constraints of the microphone and the camera, I probably shouldn't move around too much. You know, there's drawbacks too. I don't have my notes right in front of me. I've gotten super used to keeping my head still while I talk and having pretty concrete copies of what I'm going to say. So I hope you're forgiving of me as I practice being in person for presenting again. You know, I was actually at SIGCHI in July, which is the big information retrieval conference, and as we were talking, I was talking with folks about this new, sort of the new thing about being in person and how that feels different again. We were talking not just how it's different to present, it's actually different to be an audience member as well. You know, we've sort of gotten, we consume information differently. We're much more likely to multitask. It's very easy when I'm sitting at home to check email while I'm listening to a talk. It's actually even easy not to have to react, particularly because I can click a button to laugh at a joke or something like that. And so my ask is both that you be forgiving of me as I practice in person, and also that you lean in to being active audience members and practice your in-person audiencing. And you know, honestly, this tension that I'm sort of talking about figuring out what's in person and what's remote and how our actions and behaviors and the social contract is different, is like a pretty universal feeling right now. We all just spent 2.5 years figuring out remote work, and now we're trying to figure out hybrid work, and we don't know what that means. And the discomfort that we feel with that speaks to the scale of that transition. It's a really big deal, what is happening right now. And so my plan for today is to talk a little bit about what we've learned over the past couple of years, and then probably more importantly is to issue a call to action to this community. Because as we enter the hybrid work era, it's our responsibility to make sure that this transition is a positive one that lands well. All right, so, you know, prior to the pandemic, we were already in the middle of a pretty big technological shift that folks in this room were driving with the move to the cloud and the proliferation of edge devices. I see folks with their phones and their laptops, and with real fundamental advances in AI. COVID, however, provided a really important spark. It sort of took this primordial goo and it changed it and allowed us to look at work in new ways. And we did that a lot at Microsoft. We did that a lot, we've done that a lot as an academic community as well. But at Microsoft, we're pretty deeply concerned with productivity. And we have all sorts of levers that we use to understand how people get things done. We have telemetry data, we run qualitative studies and surveys, we've got customer panels. We even do like EEG studies on people's brains to see how they're reacting to things. And in March 2020, when the whole world became subjects in this giant uncontrolled natural experiment into remote work, all of the different levers that Microsoft has like zoomed with laser-like focus to understand remote work. And many of you are familiar with Microsoft research, but there's a ton of research that happens across the company. There's research that happens in our marketing organizations. There's product research that happens with the user researchers in our product orgs. Our HR and facilities teams do a ton of research to understand how things are going. And so all of these different research organizations came together in what's probably the largest research initiative that we've had at Microsoft. And we produced what I think is the world's largest research initiative into emerging work practices that we call the New Future of Work. So if you visit aka.ms/NFW, NFW stands for New Future of Work, you can find all the published research and podcasts and other information that's come out of the New Future of Work initiative. And I'm gonna highlight one particular aspect from that I think is particularly interesting, and it connects well with Barbara's talk yesterday as well. So Eitan mentioned that I know most of you sort of as an academic researcher, and that's my background, but a couple years ago, Satya, our CEO, asked me to take on this role of chief scientist. And in that capacity, my job is to drive research and innovation in our core products. So we've got amazing research that happens that's disruptive and long-term, and then we've also got research that's happening that we need to do right now in order to respond to changing conditions. And when I took on this role of chief scientist about a year before the pandemic, honestly, I wasn't set up to succeed very well. Like it is hard. The Microsoft products, like they've existed for decades. We have deep understanding about how we use them to get work done. And changing like the color of a button, let alone fundamentally reimagining the experience, is almost impossible. So I went in and I was, happy and excited and a little naive and like, yes, I'm gonna change these things. And then the pandemic hit. And the pandemic was terrifying for all of us in many different ways. And it's just, I feel the emotion to remember March 2020 and what that was like. One of the things that was sort of particular to me that I found terrifying was I was in this new role that we had made up to bring research and innovation into our core products. And in times of significant disruption, and particularly times of significant financial disruption, companies respond by looking to drive efficiencies. They get highly good at what they do, and often things like research can be seen as nice to have. And so I'm in this new role, and it's scary, and the world is sort of being turned upside down, and I'm worried I'm going to lose my job and not know what to do. And one of the things that I found really interesting, and that I think we as a community have an opportunity with, is how much COVID actually, ironically, made my job easier rather than harder. Because there's actually two ways that companies deal with disruption. One is to drive efficiencies, and the other is to lean into innovation. There's a significant change happening. How do you innovate and figure out what's happening going forward? And so all of a sudden, research has become deeply and fundamentally a part of how companies get things done and how Microsoft does business. just as like as a small little example of that, shortly prior to the pandemic, while I was in Microsoft Research, Harmon and Alex Williams and Shamsi Iqbal and I did a study on something that we called SwitchBot. And SwitchBot is something that helps people transition their attention to and from work at the start and end of the day. And part of the motivation there is I have 4 kids at home, and one of the things that I would find is, like, at the end of the day, you come home, you've got your head kind of racing from work. You get home, and then all my kids would come running and be like, "Mom, I need help with my dinner, and Kale hit me, and what's for dinner," and trying to figure all that stuff out. And I just couldn't deal with it. And so I would yell at my kids. And so we were really interested in how to help people intentionally transition their attention between work and home. And so we created a chatbot that did that, and we studied it, and we found if you transition your attention away from work, you send fewer emails and manage to engage with your family better, and probably, we didn't find this in the data, but probably yell at your kids less. And if you transition, help people transition back to work in the morning, you're actually more productive for having had that time off. And that's awesome, and that's the kind of research that we do, but it would have just sat there in a paper that we published that is nice if it weren't for the pandemic. The pandemic actually heightened this problem. Like, sure, we before had our commute time to use in order to transition our attention. When I am not even just driving from the office to my house, but I'm literally closing my laptop before the kids start screaming at me, that's an entirely more chaotic experience. That transition is needed even more. And so you see SwitchBot get immediately built into our products in the form of Teams virtual commute as a way of really trying to intentionally help people transition their attention. And I like this SwitchBot example because it's what I want to talk about, is how technology has stepped in these past 2.5 years to replace space. And now, as things are opening up, we get to start reintroducing space into the equation and figuring out how technology and space can work together to get things done. Because technology is, technology is a relatively new, digital technology is relatively new. Spatial technology is probably our oldest productivity technology. And we have been using space for millennia to get things done. Space affords social collaboration. We're all together and talking and spending time together. Space affords serendipitous and spontaneous conversations. Eitan and I just talked, and we might not have had that conversation if we weren't just co-located. Space affords interesting boundaries too. So space, when you commute into the office, provides work-life boundaries because your kids can't just come barging in on you, or your dog doesn't start barking, or the doorbell doesn't ring. Space affords temporal boundaries because when you go into the office in the morning, that's when work begins. And when you come home in the evening, that's when work ends. And we lost all of these affordances in March 2020, and we've tried to replace them. But in many ways, in many ways and in many times, in many aspects, space still remains sort of the fundamental core thing. And I would say right now, we're entering a new era in the geography of work. And I don't say this lightly because there are not like eras that start every day. In the United States, there have been maybe 5 eras in the geography of work to date. So this is a big transition we're going through. The first major era that you can think of is the Industrial Revolution. Actually, prior to the Industrial Revolution, most people worked from home. So we initially worked from home, then the development of factories and steam engines allowed people to change the way people lived and worked. We then started having the development of elevators and steel frame technology, which allowed a lot more urban density, and you have the skyscraper era. Then we have the democratization of cars, of automobiles, and people can start commuting between home and work, and you see suburbs start to develop in the post-war era. Then you see the edge city era. You can actually tell a lot about the companies that come into being too during these different eras. So Microsoft came into being during the edge city era. We exist in Redmond, in a suburb in the Puget Sound. Whereas Amazon came into existence during the superstar city era, which is sort of the most recent era that we're in, really big cities. And then now, I propose that we're entering into the hybrid work era. And one of the things that's interesting about these eras is often, there's many social and there's a lot of rich factors that go into these transitions, but they're often driven, at least in part, by technology. You wouldn't have the Industrial Revolution without a steam engine. You wouldn't have suburbs without a car. And you would not have the hybrid work era without remote communication technology. The work we're doing to create technology that allows people to communicate across time and space is going to create the hybrid work era. This is not something that we're just observing from afar. This is something we're responsible for. And so when you think about the role of the technology that we're building in that context, there's three ways that we can think about what we're building. So the first is we're building, one thing we can do is we can build technology that substitutes for space. And that's what's happened over the past 3 years. Teams and Zoom have allowed us to substitute for space. In some ways, this video camera that's recording right now is substituting for space for people who are attending remotely. And we've gotten a lot better. It is funny when I try to remember what, for example, remote meeting technology was like at the start of the pandemic. Like, the number of people who could fit on a square on a screen, it was like 9 people. There weren't a lot of people. There weren't sophisticated affordances for reacting or using chat or other ways of thinking about things. We learned all sorts of things, like even how to, like the social constructs to make remote meetings easier. It was, I remember at the start of the pandemic, it was so exhausting to not know how to end a meeting. I was used to like somebody knocking on the door or opening the conference room and that was the end. And I'm like, wait, there's no outer force. How do I just say like, sorry, that's it, talk to you later? And we can do that, and actually our technology supports that too. It'll start saying the meeting's over in 5 minutes, give you time to wrap up. So there's all these, and you can see we're making really interesting, and a lot of these affordances that I was talking about with space, we haven't yet replicated well. So we're not great at using remote technology for spontaneous conversations. Sort of the chit-chat that's sort of the hallway or pre-meeting conversation. So we're starting to develop things like that. And I think the work, for example, happening in the metaverse is going to be interesting there as well. That's a like real concrete attempt to like full-on substitute for space. But in addition to substitutional technologies, you can also have complementary technologies, and that's sort of the other area that we can think about, particularly as we're starting to be able to get together in a co-located manner. And I think the opportunity here is, one, to think about like how and when we're going to use remote collaboration versus in-person collaboration. So even things like thinking about how do you set up scheduling and how do you do the joint optimization across people for when you're going to be physically together versus when you're going to work remotely is a real opportunity. Because I've had this problem. I don't know if you've had this. And universities may be a little different than the corporate world, but I have days where I'm like, all right, I'm going into the office on Tuesday, and I show up at the office, and I'm all excited. I shower, put on pants, it's exciting. And I get to the office, and there's nobody there. Or I have like back-to-back remote meetings, so I go lock myself in my office to answer those meetings back-to-back. That's dumb. I've actually literally got into the office, had somebody pop up into the hall and be like, hi, Jamie, how you doing? And I'm like, can't talk, gotta get to my office for my meeting. which completely defeats the purpose. Like the way that I want to use my time in office is different, and we have to figure that out. You know, one of the things that people really love about remote work is the flexibility. It's been super cool. Like I'm a morning person, so I like being able to wake up early. Almost everybody else in the world's a night person and likes being able to stay up late. It's fun to be able to take walks in the middle of the day. The interesting thing is this flexibility is a deep challenge for co-location and taking advantage of connectivity and physically getting together with other people. And that's something that we need to figure out. How can we help people maintain the flexibility that they have while thinking about how to get them together and build those network effects. We ran a study that was published in Nature Human Behavior looking at the causal impact of firm-wide move to remote work on people's collaboration networks. And one of the things you see is while people are remote, your collaboration networks get deeply siloed. We sort of double down on the close contacts, our strong ties, the people we know how to work with. And people's weak ties and bridging ties atrophy. Those have a ton of value for innovation and thinking about things in new ways. That's one of the things that we're getting right now, right here, is like connecting with bridging ties, seeing things in new ways. And that's something that we want to figure out how to use space. So when you can start thinking about how to jointly optimize in person and remote, there's an opportunity there. It's actually kind of funny. Nick Bloom at Stanford has done a lot of fascinating work in this space. One of the things they found, companies, so like, also there's a huge disconnect. Employees want all the flexibility. Employers tend to want everybody coming in. And there's an interesting disconnect there. He has found that 20% of people aren't following their company policies. And generally policies are just asking people to come in and they're flat out ignoring it. More interestingly even is that how employers are responding to employees not following policy. And 40% of employers are just ignoring their employees when they don't follow policy. So we have to get better at figuring out how to help people make effective use of space, how to help people make effective use of remote time, and how to get those working well together. We actually have the opportunity to bring a ton of the value from remote collaboration into in-person as well. So like I see all of you are generally doing a very nice job of not playing on your devices, and so I appreciate you leaning into my audience request. But there is actually, when I join meetings now, I also join the meeting remotely, even when I'm in person, because I like the affordance of hand raising and that ability to sort of create lines around that. I love in-meeting chat and that opportunity to take the floor. Like you all could be reacting and having responses to this and conversations, and Harman could have shared a link to the SwitchBot paper, and there could be all this stuff going on that isn't happening. So there's this opportunity to bring some of what's good about remote to in-person. And then I'll just say the third one, because I think we're pretty familiar with the idea of substitutionary and complementary technology. The third area that I think we have a lot of opportunity around is just understanding our use of space and how we do that. Digital technology now mediates a lot more of the work that we do. It's pretty standard now for conference presentations to be recorded. I think prior to the pandemic, almost all of my conference presentations weren't recorded. Meetings are technology mediated. And that creates a real opportunity. I would love to learn how the meetings that I attend, how do I help them be more successful and drive to outcomes that I care about? There's a lot of interesting research embedded in this. There's a lot of things to understand around employee-centric privacy and privacy-preserving machine learning and differential privacy, and how do we collect data and use it in a way that is responsible and thoughtful. But I think even more so, it's really interesting to start trying to take all this activity data, because that's largely what we capture, is activity data, and tie activities in a causal manner to outcomes, because outcomes are what individuals and organizations care about. And so the more that we can start understanding data and how people use space, how people use digital technology, how people collaborate and work together, the social networks that we build, the more that we have an opportunity to really help shape work. And, you know, in many ways, I think this research community, like, our job is to be thinking about those higher order effects and what we can start doing now that this transition is happening. In many ways, like if you think about like new technologies that drive significant change, we're at the start where like the car has been developed and people are figuring out how to drive. We don't yet have the interstate system, and we don't yet have gas stations, and we're gonna, the change in work that we've seen these past couple of years will most likely pale in comparison to the change that we're seeing moving forward. And I think that's on us. And it's gonna take time, and we need to be patient. I would say, I think the current moment in the hybrid work era ahead of us, it requires a fundamental new mindset, not just in this community, but more broadly. It really requires a scientist mindset. You all are the leaders in this kind of transition. You know, and when we think about what a scientist mindset means, we think about experimentation, and unquestionably there's a lot of experimentation and learning that we still have to do to figure it out. But I think also really important is that science builds on the state of the art. It builds on what's known. And one of the things that I've seen has been a huge advantage over the past couple of years is the fact that we had decades of research into telepresence and remote collaboration to build on when we were figuring out remote work. And so I think we have a long history to build on, and we actually have a long vision, long foresight. And I think as scientists, our job is to be thinking about the long term and the externalities, and you know, what are the gas stations and you know, the seat belts we need to develop, or the different things that we need for that technology, for digital technology, remote collaboration technology, to make not just a new future of work, but a better future of work. So good luck.
We have a few minutes for questions. I'm happy if you raise your hand to bring a mic over, or you can come up, whichever you like.
Hi, this is Bala from Microsoft Research, but I joined recently. So one of the interesting consequences of this entire hybrid work seems to be that it has broken mental barriers to collaborate with someone across time zones, across geographical time. And now I can imagine if I'm someone who's an introverted person, I would be deeply siloed into interacting just with members of my own team. And if I'm a very extroverted person, then I can break those barriers. Now as we go away from, okay, I'm going away from, you know, working only from home towards hybrid work, how do you see that affecting these social dynamics, or, you know, changing the ability of different people to, now there's going to be some folks who have been able to break those barriers of remote collaboration, being able to work well with others, and then there are some folks who are going to still be sticking with their own team as a, you know, kind of a hangover of this pandemic. And do you see any efforts that are being taken to mitigate that, those barriers in working?
Yes, no, it's a good question. You've got two pieces in there. You went a different direction than I was expecting from the start, so I'll speak briefly to the collaboration across time zones too. Fascinating, that's something that we're not getting, you know, it's not, I can't collaborate with somebody in India during work hours, just fundamentally, because it's 12 and a half hours off. Like, that is impossible to do. There's actually been a ton of interesting work in this community. I think John Tung might have published his time travel proxy at UIST, or else it was Kai, but really fun to start thinking about. Actually, really excited about the breaking down of the barrier between synchronous and asynchronous collaboration and what that means, and I think actually the emerging work with AI and foundation models is going to be really relevant to that as well. So that's one area. I think there's, and you know, we should all go read John's paper and go do more stuff like that. Then the other area that you were sort of talking about is like how to start getting intentional about our collaboration networks. And this largely relates to what I was talking about being able to start looking at the activity data or the data that shows up that we can capture and understand that meaning, and actually then even start thinking about how we shape that. So one thing to think about is what do collaboration networks look like, and what collaboration networks do we want? And then we can start thinking about actively shaping those collaboration networks. And I think a fun example of how you can imagine that is start thinking about something like the feed. Right now we provide information to people via feed that, and often there are goals. We underlying feeds or search results or any way we algorithmically provide people with content, there are goals, and it may be to get engagement, it may be to sell advertising, it can maybe to get click-through. What if you start thinking about the kinds of activities that you want that underlie that? And so start thinking about, like, not only are you gonna look at content for the content that it provides, but also for the relationships that it builds. So I think there's a bunch of opportunity for us to start thinking about the kinds of networks that we build. And that's really in that, like, understanding, being able to understand what exists and shape it. It's an area we have to be super careful with, but there's a ton of opportunity.
Hello, I'm Han Lee from KAIST, Professor Andrea Bianchi's lab. I have one question. I have done an industry academic project related about physical computing in remote situation. We studied a lot with a lot of technologies, but we figure out the face-to-face situation is most efficient. So we considered about VR environment, but do you think VR environments are helpful to remote physical computing, or do you think do we need another physical tool to do this? It is in remote physical computing study.
Yeah, no, I mean, and it's a great question for this community as well, because there's so much, and Barbara talked about this yesterday, there's so much about physicality. Like, we're slowly trying to figure out and how to replicate things from physicality, but there's so much, yes, being able to see folks in a three-dimensional way becomes valuable. Being able to touch people, though, makes a big difference. Smell, all of the different things that sort of we're evolved to interact in human physical ways. My personal belief is that space is going to remain valuable for, probably in the long run we'll all live in the Matrix, but like in the foreseeable future, I think there's a lot to be said for physicality, and that's why these complementary technological solutions have such opportunity.
Hello, thanks for the great talk. My name is Frank. I am a fifth-year PhD at Arizona State. Earlier you were saying that you enjoyed being in meetings and also logging in remotely. My question is, for some people it might be really distracting just having all these things popping up. So, what are some things in your opinion that make for efficient communication, and what are things that, you believe that can be integrated with technology that makes people feel more included?
Yeah, I mean, and that's the question ahead of us, right? Like, it is super distracting as well. And there's all sorts of things that are wrong about logging into like, I join a meeting, I attend hybrid meetings, and I don't know, like, there's cameras in the room, there's a camera on my computer, I don't know where to look. I spend a lot of time setting up my home environment so the camera made me look good too. Like, the camera from my computer looks up my nose and isn't flattering. So there's a ton to be done here. And honestly, I think this is where we're going to start seeing some of these second-order effects. The ability for computing systems to consume and reason over significant amounts of data and translate it into human scale is something that's sort of going through a phase change right now. And I think that's something that we have ahead of us in the next year or two that we will see pretty significant changes on.
Hey there, great talk. I'm Ducky from UCLA, and I have a question. So this new hybrid work environment is almost like a socio-technical system, right? And we can gather data to look at how people perform. But what are your thoughts on getting that data actually adopted by the decision makers on the social side, right? Like, so, we've seen things like the more invasive boss where that may be contrast with the data may
It's a great question, and we actually at Microsoft have a whole new software category that we called Viva that we see as fundamentally related to that, actually. So in many ways, the software that we've been building to date is to help people get things done like Excel and PowerPoint and things like that. And Viva is about how do you start understanding and supporting decision-making and learning and skilling and the employee experience. So it's a deeply important, and actually any of the research that we do in this community can help feed into that. And we're it's part of what makes science so fundamental to what we're doing right now, because people make bad inferences from data too. And we need to think about how we embed good science. Like a lot of people are like, ooh, we need to experiment. And by experiment, they mean like some days I'll go in and some days I won't, and I'll see what I like better. And like we need more, to be doing things in valid ways. There's a bunch of, as you said, long-term assumptions. There's something we're calling the productivity paranoia showing up in data right now as well, where employees think they're being productive. 85% of all employees say they're being productive. Employers don't think their employees are being productive. 87% of employers think their employees aren't productive. And that's a huge disconnect. And I think some of that is, some of that I think actually relates to this activity data versus outcomes, where people are working a lot through kind of crises. We all do a lot of activity. I think about when the pandemic first hit and I was scared about my research role going, I was running around, I was doing stuff, but I wasn't necessarily doing the most valuable stuff. Once I translated that to figuring out how to help us through remote and hybrid work, like I felt meaning, and I think both for individuals to feel like they're getting things done in management, there's going to need to be changes there. So I think there's just piles of opportunity there, and I think and risk, which I've mentioned as well, that we should research here. You all can help us get through.
Hi, great talk. I'm Jian Liao from University of Calgary. I'm an undergrad student, and also, you talked about the communication silos problem, and I think I'm interested in like two problems that come after the communication. So the first one is that how would you imagine the future of knowledge sharing, and also about documentation, because there's no real source of truth, because everything gets updated everywhere. So how do we maintain that kind of like the real source of truth with knowledge sharing? And the other one is that how would you imagine in the future that, because communication can be asynchronous and synchronous, especially collaboration doesn't only happen on Zoom, it happens like afterwards. So is there a way how you can merge or switch between async and sync, and to facilitate consensus and decision making among like teams, especially like horizontal teams such as like a product team with customer success teams? So how would you propose that the future would be like?
Yeah. No, I mean, and you've got lots embedded in that. So I'll try and I could take all day to answer it. But in many ways, yes, I think what we're going to start seeing, and this is the decoupling of knowledge from artifacts. And what people are doing is largely producing knowledge, and this activity to outcome that we've been talking about is very much starts becoming how do you help support people drive towards knowledge. And then that knowledge can be used synchronously or asynchronously. We have large foundation models that can start surfacing knowledge at the right time in situ, and start surfacing, like you ask about the merging of synchronous and asynchronous collaboration. Like you think about if you're writing out content or sharing thoughts, being able to get ahead of the questions people be like, oh, Michael might be curious about this. That allows me to think through that piece before, and then that actually, to your point about helping synchronous collaboration, to them when Michael and I are talking, I'll have already thought through that and be able to make good advantage of the synchronous collaboration we're having. This is part of what I view as sort of that's the second and third order effects that we're not going to see yet. Then there's like you ask about like truth, and what is that knowledge? And I think that's going to become a challenge as well, particularly because we're getting better at having the ability of systems to communicate information, whether it's true or not, in convincing manners is getting better as well. And so that ability to think about how you help folks track down truth, cite sources, understand things is going to be a giant, wide open research problem that's worth exploring. So, yeah.
I think we're going to end with this. I know there were more questions, which I sort of circulated. So thank you. I do want you all to have lunch and come back for the rest of the program. So let's make
Hello, hello, hello. Hello. Test. Test.
个 remote talk。我没有 Lightning talk。没有 Lightning talk。Okay, I guess it's time to start this session. Hello everyone, welcome to one of the last paper session in with this year. I'm very happy to be here and chair this session. I'm Yukang Yan, a postdoc at Carnegie Mellon University. And this session is named Modeling and Intent. And we will have 6 great paper presentations in this session. And as the name suggests, we have the papers on modeling user behaviors in pointing tasks and also simulating user behaviors in several interaction tasks and also predicting users' perceived difficulty while playing games. These are some computational models for user behaviors. And also we have papers on classifying users' voice input intents and also optimizing the lighting design for the photographers. And also we even have a paper named intent. Also, of course, it's also tightly related to the user intent, inference user intent. So this session we will have a Q&A session for each paper after each paper is presented. And please feel free to come to the front if you have any questions, or you can also raise your hand so that we can bring the mic to you. So as I said, this is the last paper session, but I hope everyone will enjoy it and also enjoy the rest of the WISP programs. So I think it's time to start. We have our first talk as a remote presentation. So the presenter will be Jap Christensen from IT University of Copenhagen, and also it's a collaboration between IT University of Copenhagen and Aalto University and the Tactile Games. So basically, I will play the video for Jap, and he will join us in the following Q&A session. So I think we can start.
Hello, my name is Jeppe Christensen, and I will be talking about our paper, Personalized Game Difficulty Prediction Using Factorization Machines. This is a collaboration between both the IT University of Copenhagen and Aalto University, as well as Tactile Games. The goal of this paper is to do individual difficulty prediction. So imagine we have a group of users or players, and they have to complete certain tasks. But not all the users have encountered all the tasks yet. So what we want to do is to estimate how will they specifically find this task instead of just using the historical average of the other users. For this purpose, we use factorization machines, and we validate our approach using a case study from a mobile puzzle game. Factorization machines are a matrix factorization method where the interaction between users and items is enabled through a latent feature description. So specifically for factorization machines, for example, the target Y here can be described by some global bias, the bias for each of the features that you would typically have. So this could both be whether it's for a single user, for a single item, or maybe some more descriptive features. And then lastly, the latent interaction term here, where we have some interaction features E and the second order interactions between x1 and x2. In order to validate our approach, we use data from the commercial game Lily's Garden by Tactile Games. It's a mobile puzzle game where you have to complete a number of goals within a certain number of moves. The game is not deterministic, so the colors that drop down and so on depend on the random seed, and thus you cannot always be sure that the one tactic works in all iterations. In this paper, we consider the first 500 levels of the game, and in order to operationalize difficulty, we use the attempts that people spend to complete the level. On the right, you can see how the average number of attempts changes over the course of the first 500 levels, where easier levels require on average close to 1 attempt per complete, and harder levels require up to 7 attempts per complete. One thing to note is that the distribution of attempts is very long-tailed, so you can have, in the harder levels, players that spend upwards to 30 attempts per complete. We use data that spans around 6 months in this period here. In order to create a training set for our model, we first use all the data up until a given point, which is the observed levels for all the players, and then we take the data from the remaining 99% and all the levels that we have available. We test our methods on the remaining 1% of the users after level 150. What we see is that in order to beat our baseline that consists of the average of the other players in the training set, we need around 20 to 30 observations in order to beat that. We also see that random forest, which is the purple here, fares better with fewer observations, but as we include more and more data, it performs worse than our factorization machine model. Lastly, we can also see that the effect of including additional data, such as some player features or level attributes, helps the prediction of the factorization machine. In addition to investigating how many observations of the players we need, we also provide an interpretation of the model parameters. In this case, we consider the two-factor model, which provides us with 3 parameters to explain the variable biases, WI, and the 2 latent factors, V1 and V2. For the variable bias, WI, we first note that for the levels, the average number of attempts is strongly correlated with the level bias. This suggests that the level bias here captures the average difficulty of the level. For players, we note that the biases are centered around 0 and therefore capture some kind of variation or small variation between the players. For the first latent factor, V1, we note that for most of the levels, the latent factor is above 0. This suggests that it captures some kind of intrinsic variability of the level, which is supported by the graph on the right. It shows that the variation in attempts increases compared to the mean of the attempts as the latent factor increases. Furthermore, tutorial levels are clustered to the left at low values of the latent factor. Common to many tutorials in the game is that they are deterministic and use specific random seeds to ensure similar experiences. For the players, the latent factor instead captures some kind of skill or their ability to deal with stochastic elements. The larger the absolute value of the latent factor is, the more susceptible they are to random elements of the game. The sign then indicates whether it increases or decreases the number of expected attempts they will use. For the second latent factor, V2, the results are less clear. For both the levels and the players, the values are all centered around 0, and on the graph to the right, we can see a clear dependence on both the level number and the average number of attempts on the level. We therefore interpret the parameter as some kind of time-dependent descriptor, which for the players captures their ability to learn over time relative to the rest of the player base on these levels. Overall, we find that factorization machines provide an accurate and scalable method for personalized predictions of the perceived difficulty. The method performs better than the baselines using either historical averages or random forest, especially once more observations are included. The method is also game, task, and domain agnostic. In any problem where user-item interactions can be described using a multiplicative or divisive way, factorization machines can be used to capture these latent interactions for any kind of regression target, such as time taken or similar. Lastly, it's also possible to include additional data, which could be tags, labels, time, user features, task attributes, and so on. However, one thing that has not been considered is how to deal with the cold start problem, which is when there are no observations of either the player or the levels. While additional data can help this issue, future work can look into how to best deal with this problem. Thank you for your attention, and unfortunately I couldn't be there in person, but I should be in the chat now to take questions.
Hi, Jeff. Yeah, thank you. Hi, nice to meet you. So this is the Q&A session. If you have any questions, you could come to the front to ask, or you can raise your hand. We will bring it back to you. Yeah, Jackie, please.
Hey, and this is Jackie Young from Stanford University. Maybe it's a silly question, but like I wonder, so you use the number of attempts to measure the difficulty of the game. I'm worried that whether some players will never complete a level, so you don't really have their data there. Like for example, they stop trying after 3 trials.
That's a good point. So the question of basically how to operationalize difficulty and whether using the attempts that they use is the correct thing or the best thing. It is, it does require them to complete the level. Generally, they complete it within a number of attempts. Like it doesn't go much higher than 10 attempts per level, for example, per player. So you do see some that never completed. But I guess because of the scale, most people generally either complete it or it doesn't really. It just counts up towards the number of attempts they spend. I think it's still you could use it as a maybe minimum number of attempts instead to whether they complete it or not. But it's a good point. You can play around with it, and the exact definition depends maybe on what you find desirable. But yeah, I hope it mostly answers your question.
Right, thanks. Just to clarify, so this is not a lab study that you invite people to do this in your lab, but rather than this is collected in the wild, right?
No, so there might be a difference if you want to do this in the lab and this is basically in the wild observations. So we just use it as it is, that data.
Got it, cool, thanks.
Yeah.
But yeah, it actually shouldn't, I don't think it would matter too much if you use it in the lab. It would just maybe change your definition slightly. So have that as a caveat to your data.
Yeah, because like in the lab it's more natural, in the wild it's more natural, but in the lab you can ask them to make sure they finish the game rather than stop. But
yeah.
Very cool, thanks.
Yeah.
Yeah, thank you. Any other questions? So maybe I can also have the privilege to ask a question. I am curious about the learning effect of the users. Like, I guess the users will improve their skills after more trials of playing with the games. At some stage, do you think that the user will turn to be a new user or a different user in terms of skills? So does your algorithm actually capture this performance improvements or difference?
Yeah, that's a good point also. There might be some different rate that the players learn how to play the game. We sort of see it being captured in the second latent factor. And I think the more factors you add, the more these factors kind of describe these secondary and tertiary effects of how the player adapts their play style. It's not, it captures, it does capture some kind of learning rate of the player and how well they do it. But I think in practice you would maybe use it or retrain this. If you want to use it for in a game, you would retrain it every day. But of course, then the factor changes of the players also. But it has some implicit way of learning this rate, which is captured more and more in the latent factors as you add more and more latent factors.
Got it. Thank you. I think that. So yeah, we will. Thank you, Jeb. We can do this another round of applause for Jeb. And I think if you have further questions, you can also post it in the Discord channels so that you can communicate more. So yeah, thank you. So
thank you.
sorry that we need to switch to a different laptop now.
So our next paper will be based on hierarchical pointing models presented by Han Zhao from Stony Brook University. And one note is that Han is open to a summer internship in 2023. So if you are hiring, please consider Han.
Okay.
And take it away.
Okay. All right, thank you. Hello, good afternoon, everyone. So this is Han Zhao, a PhD student from Stony Brook University, advised by Professor Xiaojun Bi. Today, I will introduce our work, Bayesian hierarchical pointing models. Fitts law relates to the movement time MT of a pointer to the pointing of the Fitts law relates to the movement time of a pointing task to the pointer travel distance A and target with W. Fitts law is probably the most important model in HCI and has been widely used for input device evaluation and interface optimization. Despite its success, however, it has two shortcomings. As you can see in the figure, so the variance for each ID is shown. But Fitts law only provides the point estimate, namely the mean movement time, but shows no information about the variance and distributions. It also fails to quantify the uncertainty of parameters. Which causes low accuracy in estimating parameters and making predictions. So another shortcoming is like the approach for parameter estimation. The most typical approach for parameter estimation are pool model and individual model. As you can see in the figure, so the regression line for each user is different. But pool model treats all users as the same pool and ignore individual difference. This actually causes low accuracy. The individual model treats all like each user's data like separately, and creates one model for each user separately. Sorry about that. So a little nervous. This actually fails to leverage information from other users. And the model is easy to be influenced by outliers. To solve this problem, we propose Bayesian hierarchical pointing models. Our contributions are twofold. First, we extend Fitts law to be a Bayesian hierarchical model. Bayesian model is different from classical models, for it uses probability distribution to quantify the uncertainty of parameters. As you can see in the figure, it estimates parameters for each user I, but these parameters are related, so they follow a distribution. It is also called partial pooling with many advantages, since when it estimates one user's parameter, it can leverage other users' information. This method is commonly used in cognitive modeling, psychology, and nuclear safety, etc.
But this is really used in human-computer interaction. So at this time, we introduced it into HCI community. Second, we investigate the effects of non-informative prior, highly informative prior, and weakly informative prior, which are shown in the Bayesian hierarchical model as mu theta and sigma theta. Next, we show how to extend Fitzroy to be a Bayesian model. The typical approach to predict the distribution of movement time is using Gaussian distribution. The graph on the left showing that the distribution of movement time in blue. Now we apply several different models to predict this distribution. As you can see, the Gaussian distribution in black cannot resemble the distribution of observed movement time. Also, Fitzroy movement time has a natural boundary of 0, but the boundary for Gaussian is from negative infinity to positive infinity. So previous work has shown that the distribution of movement time for a given ID is positively skewed and can be modeled by log normal, gamma, extreme value, and X-Gaussian distribution. So in our research, we choose X-Gaussian distribution, which is the sum of independent Gaussian and exponential random variables. For Fitzroy, in order to obtain the distribution of movement time, we need to calculate the variance. It has been observed the variance of movement time is not constant. Previous study has shown the variance increase if ID increase as the variance of sub-movement time accumulates during the process. So similar to our last year's paper, variance and distribution models for steering tasks, it shows that the variance of movement time is quadratically related to ID. So ID is the index of difficulty. So we adopted this quadratic variance model since both Fitzroy and the steering law reflect the regularity of human motor control system. Now we can build a Bayesian model using X-Gaussian distribution. The formula is shown for X-Gaussian distribution, and it has 3 parameters: the location parameter mu, the scale parameter sigma, and the shape parameter lambda. The mean of X-Gaussian distribution is proportional to ID, which is Fitzroy. So the variance of X-Gaussian distribution is proportional to ID square, which is the quadratic variance model. So we can plug in these 2 values into the parameter formula and fit the model using observed data. Next, we show how to extend Fitzroy to be a Bayesian hierarchical model. Bayesian hierarchical model has 2 stages. In stage 1, we assume that MTI follows X-Gaussian distribution, which is governed by the parameter theta I, where I is the index of user. In this model, theta I consists of AI, BI, CI, DI, and KI. In stage 2, we assume that theta I follows a distribution governed by the hyperparameter theta, mu, and sigma square. After we build Bayesian hierarchical model, we show how to set prior distributions for our model candidates. The prior parts of Bayesian hierarchical model are shown in a figure. For non-informative prior, we inform null information from the data and use uniform distribution for all parameters. For highly informative priors, we adopted the mean and standard deviation from a previously collected JGP pointing dataset. Weakly informative prior is something in between. we set the prior same as highly informative prior, except that the standard deviation of prior are much wider. Highly informative prior is chosen for it incorporates the knowledge from previous research. Weakly informative prior is chosen since it incorporates partial knowledge from previous research, but still provides enough flexibility for Bayesian inference to modify the parameters based on the observed data. Next, we carry out evaluation on MOS dataset. MOS dataset is a cursor-based pointing task which contains 12 participants and 8 conditions. We evaluate 3 model candidates and investigate 3 prior distributions. In order to make the comprehensive model comparison, we perform 4 evaluation tests. In all data tests, we fit each model with all data. In leave one user out cross-validation test, one user's data will hold for testing, and the rest of data were for training. We repeat this procedure 12 times until each of the 12 users' data will hold for testing once. In leave ID out validation, movement time for 4 randomly chosen ID of task will hold for testing, and the rest of data were for training. In small training data test, we train the model with only 5%, 10%, and 20% of data, and tested them on the remaining 95%, 90%, and 80% of data respectively. So as you can see in the distribution fitting figure, so in all data tests, our results show that both individual model and the hierarchical model more accurately fit the distribution of movement time than pool model. So as you can see in the mean movement time fitting figure on the left and the distribution fitting figure on the right, in leave one user out cross-validation test, our results show the Bayesian hierarchical model more accurately fit the mean and distribution of movement time than pool model. Individual model cannot predict the distribution for unseen users since it has no data to start with for unseen users. In leave ID out validation test, our results show that so both individual and the Bayesian hierarchy model look very similar to the distribution of observed movement time and perform much better than pool model. In small training data test, our results show that Bayesian hierarchical model more accurately fit the mean and the distribution of movement time than individual model and the pool model. So in this research, so we first extend Fitts law to be a Bayesian hierarchy model. The formula and the distribution of X-Gaussian distribution are shown here. The mean of X-Gaussian distribution is predicted by the Fitts law, and the variance of X-Gaussian distribution is predicted by a quadratic variance model. So for each user, so this model actually has 2 stages. In stage 1, each user's data is like a learn, is predicted, is learned in the data. And in the second stage, actually, these parameters learned from the first stage are related and follow a distribution. Second, Bayesian hierarchical model of Fitts law is a more principled approach to model the pointing task than pool model or individual model. What also shows that the weakly informative prior is much more, it's a more appropriate prior to the parameters than highly informative and non-informative prior. So you can refer our paper for more details. That's all for my presentation. Thank you. I'm open for further questions. Thank you.
Any questions from the audience? So maybe I can start with one question of mine. It's great to see that the hierarchical model is more principled in fitting the data. I'm curious about how these improvements in fitting the data can be transferred into the task performance improvements in some real applications or tasks. And in other words, do you have some examples of applications that we can leverage this model?
Yeah, that's a very good question, actually. So since we know that the Bayesian hierarchical model like more accurately predict the distribution and the mean of like movement time than pole and the individual model. So Bayesian hierarchical model actually can be like a benefit the model-based input device like evaluation and interface optimization. So for example, if you have interface, so previously you can only predict the mean using Fitts law. Now you can use the Bayesian hierarchical model to predict the distribution of this movement time. Also, because this is like a probabilistic like method. Yeah. Thank you.
Due to the time limit, maybe that's all for this Q&A session. Let's thank Han again. And also, just a reminder, if you are having for internship, please consider. Thank you. So our next talk will be like interactive tensor transformation synthesis, which will be presented by Tianyi Zhang from Purdue University. It's also a work in collaboration with Purdue University and also University of Michigan.
Thank you for the introduction.
Yeah, take it
All
away.
right, just give me a few seconds. All right. Hello, everyone. My name is Tianyi Zhang, and I'm an assistant professor in the Department of Computer Science at Purdue University. Today, I will talk about intent interactive tensor transformation synthesis. And this work is done by a group of amazing undergrad students at Purdue and also University of Michigan. Because they all graduated, so they cannot be here today. So I'm presenting on their behalf, and all the credit should go to the students. All right, let's get started. So deep learning has become widely used in the industry, and a lot of programmers, they actually want to advance their career and acquire this skill of deep learning. But deep learning frameworks like TensorFlow and PyTorch often come with a very steep learning curve. Kerry Chai and Philip Guo actually did a large-scale survey in 2019, and they identified two main learning hurdles. One is the lack of understanding of the mathematical computation inside deep learning, and the other one is because of the cryptic API design in these frameworks. And programming in deep learning is quite different from traditional programming, such as web development, right? And one big difference is that tensors, or multidimensional arrays, as many of you may call it, are the first-class citizen. And those tensors are flowing around the entire pipeline of deep learning, from data pre-processing to model evaluation. So programming in deep learning is essentially about writing a bunch of tensor transformation functions. For example, reshaping the output tensor from one layer to fit the input of the next layer, or normalizing the tensors for feature scaling, etc. And let's look at an example. This is a Stack Overflow question about how to slice a tensor based on another tensor. So suppose we have two tensors, x and y, and now we want to basically to select the values from x where the corresponding values in y are greater than 1. So how should we do this? If you are a regular programmer, you may think about, let's write a explicit for loop to iterate over these tensors and check. But this is not a good option in deep learning because it's not very efficient to have an explicit loop for large tensors, and it's also very hard to parallelize. So the correct solution here is to use the Boolean mask operator provided by TensorFlow. If you are not a TensorFlow expert, this is actually very hard to think of, especially given there are 500 tensor operators from TensorFlow. And even if you know this API, right, it's also very hard to make use of it because you have to make sense of the arguments required by this API and also make sure the tensor type and shape are compatible with each other. So our solution is to leverage program senses for tensor transformation. So user only need to provide a natural language description and some input-output examples to specify the desired transformation, and the synthesizer will automatically generate TensorFlow code on behalf of the user. And the main HCI challenge we address in this work is program understanding and user trust. And this challenge is exacerbated in deep learning because the tensor transformation code often involves very complex linear algebra calculation and also cryptic API usage. So even if you give the correct code to the programmer will spend a lot of time to even figure out whether it is indeed correct or not. To address this challenge, we actually propose 3 normal features. The first one is, we call it data flow visualization, and this visualization will help users to understand the individual internal computation steps in a tensor transformation. And the next one is element-wise data provenance, where users can easily figure out which part of the input tensor contribute to which part of the output tensor. And also, we provide in situ program edit and validation, where users can easily tweak the synthesized code and validate the other alternative options they have in their mind. Now let me walk you through the features in our tool with a very simple example. Let's say a user wants to set all the maximum elements in a tensor to 0. So you can type in the input-output example and also a natural language description. You can also specify the desired and undesired operators you want the synthesizer to consider in this computation process. But I will leave it now and revisit this later. And then the synthesizer will quickly find 3 solutions. And for each solution, intent will generate a data flow diagram that visualizes the individual computation steps in this transformation with intermediate input and output results. And in this way, you can easily find out how an input tensor is transformed into the output tensor step by step. And you can also click on individual elements in the tensor to figure out which elements in other tensors contribute to the production of this element. If some operators look promising or some operators doesn't make sense at all, you can also mark them as desired or undesired to prune the search space for the synthesizer. Oh, yes. And understanding is not the end of the story yet. Programmers typically want to do additional testing and validation to really confirm their understanding or hypothesis. So they can easily do this in intent by adding new test cases. And intent will automatically run the synthesized solutions on this newly added test cases. And they can also tweak a program generated by the synthesizer and evaluate on the existing test cases. Here I'm basically replacing the greater operator with equal, and you can see this alternative option actually fails the given test input. To evaluate intent, we did a user study with 18 graduate students from Purdue CS department. And those participants actually have different levels of programming skills and also different levels of familiarity with TensorFlow. And we also compared intent with another tensor transformation synthesizer called TF Coder. And this is a really a head-to-head comparison because our synthesis algorithm is built on top of a TF coder. And we also create a similar user interface for TF coder to ensure that people are not influenced by the visual design of our tool. And in each study session, we ask participants to finish 2 tensor transformation tasks, one with intent and the other with TF coder. And we randomly select 2 out of 3 tasks from 3 real-world tasks on Stack Overflow and also an internal Google forum. And we found that when using intent, more participants actually finish the task successfully with only half of the time. So we are curious, why this such a big time reduction? We actually identified 2 time sinks when using the baseline tool. First, we found that users constantly search online and read documentation and the Stack Overflow posts to understand the TensorFlow operator. But when they have the data flow visualization, they barely did this. And also, users often switch to Google Colab to set up a testing environment and validate a synthesized solution. And the in situ program validation feature in intent actually eliminated this context switching overhead. Participants also felt more confident about the synthesized code when using intent. As one person said, intent actually is very helpful to understand which function in a tensor transformation contributes to the part of the computation. And it's particularly useful for complex transformations. And the participants also filled out a NASA TLX questionnaire after each task. And we found that participants felt much less mental demand and stress when using intent. All right, the key takeaway. So we have come a long way in program synthesis from the very first program synthesizer for Lisp in the 60s to GPT-3 and GitHub Copilot, which are released last year. There has been huge improvement in the program synthesis algorithms and also the models. But there are still a lot of usability challenges in adopting program synthesis. Here I actually also want to point you to another work we did this year on the usability of GitHub Copilot. And we found similar programmer understanding and user trust issue when people use Copilot. So I think this is really the time that we start thinking about the adoption barriers of program synthesis rather than the algorithm itself. And really leverage our HCI expertise to design for the adoption of program synthesis in different domains. So that's all I have today. Feel free to scan this QR code and get a free copy of our paper. There are many details that I didn't really get the chance to talk about, like the synthesis algorithm, what kind of models we use to infer user intent. But you can find all the details in the paper. Thank you all for listening, and I'm happy to take your questions.
Any question from audience? Okay, I can also start with mine. So it's really a great work. I think it's very helpful for users, especially with the users with less experience or knowledge about TensorFlow. I'm curious about maybe also that's a generic question about the data sets program. Like, how do you think it will help the users to gain knowledge about the TensorFlow and finally becomes an expert? Because actually we learn from checking documents and trying out a lot of them. Do you think that intent will speed up this process, or it will help users learn?
Yeah, I think the intent is definitely, by the way, thank you for the great question. I think it's definitely a great tool for teaching people about the tensor transformations and especially the linear algebra calculation behind it. Because you can see that we have this data flow diagram with this intermediate steps. And especially this data provenance feature can help them understand behind this math equations, how does this computation is done exactly, right? Which value flows to which value in the output. So I think it's going to be a great teaching tool as well.
Yeah, thank you. I really like the example that you show how users confirm it is correct or not. That's in the paper also.
Yes.
Yeah, so maybe for more details, please refer to the paper. Any
Justin from UC Berkeley. I loved your talk. It was really great. I especially loved the conclusion where you were sort of gesturing at the broader picture. Based on what you learned from intent and maybe some of the other work that you've done, what do you think is some of the biggest, most pressing open questions in HCI for program synthesis?
I think the biggest issue is still communicating the synthesized code to the user, because essentially a big audience or target user group of this program synthesis work are end users who know little about syntax and also the semantics of a programming language. So it's really important think about what are the other possible ways to communicate the meaning of a program synthesized code for the end users to understand them and validate them.
Awesome, thank you. Very exciting.
So thanks Kenya again, and now we will have the next presentation. Our next talk is named Breathing Life into Biomechanical User Models, that will be presented by Alexei Ikala from Aalto University. This is a great paper about how to simulate user behaviors in several interesting interaction tasks. So I think take it away.
Okay, thank you. Okay, thank you for the introduction. My name is Alexei Ikala, and I'm a PhD student at Aalto University. And in this talk, I'm going to present our approach on modeling and simulating users and interaction. And as you can see, we have quite a big group behind this project. And in this short video, you can also see the kind of interaction kind of user models I will be discussing in this presentation. So we have a biomechanical user model combined with some perceptual capabilities, such as an egocentric camera vision that is located in the eye. And you can see in this lower right corner the output from that camera. Okay. So simulated users, what are they good for? Well, imagine, for example, that you're working on an iterative design process where you may need to have to change some of the parameters. And every time you change the parameters, you need to run a user test to validate or evaluate those changes. And over time, this builds up to a lot of user studies. And as you may know or have experience with user studies, they can be laborious, tedious, they take time. They can be also expensive. And if additionally you're also collecting data from the participants during those user studies, depending on what kind of data you need, you may need to use a lot of different kind of sensor rigs, such as when you're collecting motion capture data, as my colleague here in this video is demonstrating. It can be quite awkward. So if using really humans is messy, tedious, expensive, how about we use simulated users for the user studies? And user modeling actually has long traditions in HCI, but unfortunately, especially when it comes to biomechanical user models, the previous models can be quite inaccurate. For example, they may not have enough degrees of freedom. They may not be muscle actuated to actually capture the actual human movement dynamics. Also, there may not be perception models included. So, for example, in case of movement, there may not be perceptual control over the biomechanical model. And this all comes down to the previous biomechanical models being kind of crash test dummies in the way that you need to pre-specify in advance how they move. For example, by inputting the control signals to the actuators, or estimating in advance the control signals for the actuators. Or you may need to collect human data, for example, using motion capture, and then do your analysis based on that human data. So these are not generative models of movement. Okay, so if the previous models were kind of like crash test dummies, then we would like to breathe life into those models such that they are more applicable to a wider range of interaction modeling problems. And this is where our research comes in. So for the first time, we have presented these biologically plausible, muscle-actuated, high-fidelity biomechanical models and combined them with perceptual capabilities. And these user models are able to learn to interact with their environments, especially if they include physical device models. And this kind of, our aim is to push forward this paradigm of designing, developing, and testing user interfaces with simulated users. Okay, so a couple of words of the actual implementation. We wanted to keep the framework or the structure of our framework as modular as possible, so that it would be, you could flexibly change any parts of the problem that you're trying to model. So the first part, the first component is this interactive task definition in the green box. So this contains this defines the interaction environment itself, including any possible physical device models that there may be. Then we have the muscle-actuated biomechanical model and related perception models. And all of these models are components are bound together with a control policy that is learned through simulations via deep reinforcement learning. And the advantage of using reinforcement learning here to learn these control policies is that it's quite a flexible way of defining this problem of modeling interactions. So all we need to do basically is define the states the user model can be in, the actions the user model can take, and the reward the user model receives by interacting with the environment. And here I have this simulation loop. So this kind of describes what happens during the training process. So we have the biomechanical model. It interacts within the environment. And since this is a simulation, we have full, complete knowledge of the state of the whole world, of the whole simulation. So this full, complete knowledge is passed through the perception models, which act as kind of a filters. So the perception models dictate what kind of information passes through to the policy. So the policy, in this case, being a neural network, outputs an action, muscle controls, and this action, again, defines how the user model behaves or interacts with the environment. And as the user model interacts with the environment, it receives a reward. This is a task-specific reward. So the point in reinforcement learning is to try to learn such a control policy, those muscle controls that maximize the expected cumulative future rewards the user model receives by interacting with the environment. And in our paper, we had 4 tasks, 4 different interaction tasks into which we put our simulated user. And the point of these tasks is just to show that our simulated user is able to learn these motor perceptual control policies through reinforcement learning, just based on, or in an emergent way, just based on the task-specific reward functions that we have defined. So the first task, pointing, pretty standard. So in this case, the observation that goes to the policy network or the outputs of the perception models is proprioception, joint angles, velocities, accelerations, and muscle internal states, and the depth image from the egocentric camera, which you can see here, although this is an RGB image, not the depth image, but you get the idea. And the reward may look a bit complicated, but basically it just tells that if the simulated user hits the target, give a high reward. Hitting the target meaning that the user keeps its fingertip inside the target for half a second. And otherwise, give a small negative reward, which is shaped in a way that the further the fingertip is from the target, the more negative the reward is. So all this is just to say that the user model should put its finger inside the target as fast as possible to gather as much reward as possible. And we did some analysis on the pointing movements, and we found out that the movements follow Fitts law, and we also had some more comparisons to human data in the paper. So the second task then is tracking. Again, observation, we have the proprioception, and we have the depth image, but at this time, the user also gets an image from a previous time step, so that it can have some sort of an idea of how the target is moving. And here now the reward is actually quite simple. It's just a negative of the distance between the fingertip and the target. Again, meaning that to get as much reward as possible, the fingertip needs to be as close as possible to the target. Then the third task, choice reaction. Here the observation, again, quite similar, except instead of a depth image, we get an RGB image, because in the task, the user has this screen in front of it, and based on the color of the screen, it needs to push the correct button. And the reward here is pretty similar to the one we used in pointing. Okay, then the fourth task, which is by far the most complex task that we have so far used. Here the observation, again, pretty similar to the earlier ones, except now the user also has a force sensor in the fingertip so that it knows when it's touching the joystick. And the idea in this task being that the user needs to control the velocity of the car by tilting the joystick forward or backward and steer it inside the target, the green target box. And as you can see, the reward here is looking a lot more complicated now. It's a component of a combination of 4 different components. 2 of the components related to the distance between the fingertip and the joystick, or the car and the target, and then some extra bonus terms for doing specific things. Okay, so all of our code is open source. We aim to make this code as modular as possible, so that you are able to flexibly or easily extend it with your own biomechanical models, or own task definitions, or your own perception models, whatever you want to do. And the idea is that we build these simulators that are easy to share. They are Python packages. And they also implement the OpenAI gym interface, so they are easy to plug and play into any RL library. And the kind of biggest challenges as I see them at this point. So how to come up with these reward functions. As you saw, when the task gets more complicated, the reward function also gets more complicated. So how do we effectively design reward functions that actually work? It's a big question. And also we did do some comparisons to human data. It's still unclear to what degree these simulations actually are faithful to human performance. And the used biomechanical perception models we had, they are still relatively simple, so expanding those would be great. Okay, so then the summary. In this paper, we presented these muscle-actuated biomechanical models combined with perception models, and they learn to interact with physically simulated devices. And these generative control policies are trained via deep reinforcement learning by maximizing task-specific reward functions. And finally, here's a link to the GitHub repository. Please go check it out, and hopefully it will be useful to some of you. And with that, I conclude the presentation. Thank you for your attention.
first. Very nice presentation, very good work, and also nice that you open sourced all the code. I have a question with regard to scalability. So do you already have a guess how the training time of the reinforcement-driven algorithm scales in terms of either more complex perceptual models and more complex tasks, for example, navigating through a GUI or something like this?
Yeah. So the training time for the pointing task, for example, was around 1 day or 2 days, something like that. And then for the parking task, it's already 3 days, 4 days, something like that. But one of the issues here is that every time we do the learning, the learning starts from scratch. So every time we do it, the user needs to learn how to move its arm. So one of the things we're currently researching is how to move on to hierarchical models so that we can learn one low-level policy to control the arm first and then do further training for the actual tasks. Especially if we increase the degrees of freedom of the model, the number of muscle actuators, the training is going to get a lot more difficult, and I'm afraid the scalability will be an issue. But thank you.
Thank you. No one has a question, I would ask another one. How easy is it because if we take a look at Fitts law, in the previous presentation we saw that it's highly dependent on personality. How easy is it in your work to adapt the different perceptual models such that, for example, you can make them better applicable for older age people or younger people?
Yeah, so if you have an idea of how to implement that within the perception models, extending, or the coding part, extending the perception models is easy, but of course, like having the sort of what kind of an effect aging has, for example, I don't know how that would be programmed into, but implementation-wise, it's possible, but conceptually, not sure.
Okay, thank you.
Maybe I have one more question for this. So, as we know that the human perception or control is not that perfect as the simulated user, do you consider introducing some simulated noise in user control and also perception?
Yeah. So all the observations we've used so far are perfect. So there's no noise included. Including noise is something we will look more into, and also just expanding the perception models in general. For example, here the eye or the camera is fixed in one direction, so having a camera that moves, for example, that sort of extensions are sorely needed.
Thank you. And Alexei again for the great talk. So our next presentation will be dual voice speech interaction that discriminates between normal and whispered voice input. That is a single author from Jun Yukimoto, University of Tokyo. So take it away.
Okay, thank you very much. My name is Jun Yukimoto from the University of Tokyo and Sony Computer Science Laboratory, Kyoto. And so this topic is dual voice, speech interaction that discriminate between normal and whispered voice input. And in these days, the quality of voice input speech recognition is quite high, and we can use for controlling smart devices by voice. But recently, some writers tried to using speech for text input. So at the beginning, the opening keynote session, Mr. Te-chan talked about speech communication and their era of writing communication. But I think the boundary between speech and writing is now it's quite close, and many writers are using speech input for text input tools. But however, if you seriously try text input by using speech, some problems. So maybe show, this is an example, typical example, Google document using speech input and try to some document. Sorry, there is no audio as usual. it's not the demonstration silent speech. It's just,あれちょっと待ってください。さっき確かめたんですけど。Yeah, I selected. It's not. Yeah, yes, I did. Or maybe I can just the normal, yeah. So.
No pictures or canvas.
Okay. So I'm going to use the real microphone for both my presentation as well as speech. Oops. So sorry about this. So if we want to try to use text input, so by using like Google Doc using speech input.
No pictures or conversations in it.
So that part is it, but
comma, double quote. And what is the use of a book? Comma, double quote.
Okay, so in this case, so this person is trying to use a double quote, but this recognizes the different word. And also, this is rather difficult to correct the misrecognition, because I would say something and misrecognize, and there is no way to re-edit or correct errors. So
no pictures or conversations in.
Okay. So I think this is a similar situation that when we are using the keyboard, and the keyboard has alphabet buttons, and also some command keys, as well as the numeric key or symbol keys. But for the current audio speech recognition, it's only provide this part. So the speech recognition can recognize the alphabet, but there is no easy way to recognize symbols, or there is ambiguity between symbols and normal characters. So when I want to input double quote, but I think if I want to literally write double quote, it's rather difficult to distinguish symbol double quote and letter double quote. And also there are no command keys, so for recognize for correct errors. So idea is very simple, and we can provide a normal voice for the normal text input, while the whisper voice as a command. Okay, so I can enter something, but this is for the computer. So okay, so idea is quite simple. And also you can see the spectrogram. So maybe it might be possible to distinguish the normal voice. So visually different. So the neural network can distinguish these two. So the architecture is also very simple. So there is a kind of speech input system, and there is a whisper voice and normal voice classifier that classifies the normal voice part and whisper voice part. And there are two recognition system. One for the normal voice recognition. So we can use the normal, the standard voice recognition such as Google Doc speech recognition. And also we provide a custom whisper voice recognizer. And then these two streams can be combined in the tools. So the normal text for the text input and other whisper voice for the command. But we can also combine it's a way to make a shift key or something, a mode change of speech. So we can create a lot of different applications. And also this is very simple, and we cannot use other sensors or other devices. So just a normal microphone for text speech recognition, and then all the software can do it. So this is very simple text input device using dual voice. So please note that I think whisper part is very low, so please concentrate. And also the above line shows what is recognized by the whisper voice.
Alice in Wonderland. Chapter 1. Down the rabbit hole. Alice was beginning to get very tired. of sitting by her sister.
So there is error. But no good candidate, so we are deleting.
Of sitting by her sister. On the bank.
Okay, so something like this. And another example is the emoji input. And have you considered inputting emoji by only using your voice? So it's not so trivial.
Good day today. Smile.
Error. So,
emotion. I don't like this. Angry.
So in this case, the word emotions in emotion is for the emoji input. So I think you got the idea, and it's quite simple. So to realize this kind of interface, we need two types of neural networks. The one is for whisper speech recognizer, and the other is for whisper normal classifier. And for whisper speech recognizer, we are using the self-supervised learning speech input system known as Web2, Vec2, or Hubert. So this is, I think, developed by the Meta AI research, and it's a self-supervised learning end-to-end speech recognition. So this can automatically or self-supervise of the feature, audio feature, speech feature, by just adding the lot of example whisper speech and normal speech. And then the small amount of transcribed corpus can be used for actually create a speech recognizer. So we tested this, and the results are quite good. And also, this is interesting because unlike normal speech recognition system, so this is directly takes low speech input wave, and then there is a feature extractor like this one is automatically trained for extract the speech feature, and then this can be used for speech recognition. And in our case, this speech feature extractor can also be used to recognize or classify whisper and normal classifier. So we can add a few additional layers such as average, pooling, or layer normalization, and just fully connected, very, very simple layers. And it becomes a very high speed and very accurate whisper and normal classifier system. So like this. And then at this moment, so if we extract the feature of just after the feature extractor, and the classification like this one. So this is TSNA visualization, and red represent whisper, and the blue represent normal. And so this kind of separated, but still there are ambiguity. But after these some additional layers, so it's very clearly separate whisper normal voices. And also this is kind of example of. So this is recognition classification.
A quick brown fox.
So the white bar represent the classification results. So it's very clearly recognize or distinguish whisper normal voices. So actually this is very simple, but we can also consider other kind of applications. So I presented kind of text input with whisper command, but when I am talking to the normal voice, so using a normal conversation, but I can get, Alexa, please. So I can very easily distinguish the normal conversation and the computer conversation. And the other example is speak as two avatars. So like I speak as one avatar, while speak as a second avatar. So maybe I can show some example. So suppose that you are doing the Zoom meeting, and during conversation with the other person, and you want to consult the computer database or your schedule by using whisper voice, something like this.
Okay, let's talk more about this in the next meeting. Computer, show me my calendar. Or how about next Wednesday afternoon?
So it looks like, so I can suddenly give a command to the computer and get information. But in this case, the whisper voice also transmitted to the other end. So the other person also noticed that I'm whispering. So then I can mute this part, but still my lip is moving. So I can use other technology like wave to lip replacing and try to make this part is silent. So this is not complete, but this is the result.
Okay, let's talk more about this in the next meeting. Or how about next Wednesday afternoon?
So something like this. So RIP is still moving, so not complete, but I can have a natural conversation, but at the same time we can have a computer conversation with whisper voice. The other example is like speakers to avatars, two persons. So I cannot create complete avatar, but you can get the idea. So I can speak like two persons. So this is original.
What did you say? I said we could have everything. We can have everything. No, we can't. We can have the whole world. No, we can't. We can go everywhere. No, we can't. It isn't ours anymore.
Okay, so this is the normal whisper. And then we can voice convert from using voice conversion of whisper to other person's voice. So then we can create a two-person's voice version. So input is exactly the same, and the system can make this kind of conversation.
What did you say?
I said we could have everything.
We can have everything.
No, we can't.
We can have the whole world.
No, we can't.
We can go everywhere.
No, we can't. It isn't ours anymore.
So I can represent two persons. So maybe in a metaverse or something, so if here I want to be two avatars, so I think like a one avatar, other avatars. So we can behave like two persons. So this idea is very simple, but I think this is I think important the improvement of human-computer interaction. So if you compare the single touch and multi-touch, so we are deal with a single touch, but in the natural environment or real world, we are very naturally have the ability to using multiple multi-touch manipulation. And similarly, so the voice input forced to do a single voice, but we have a natural ability to distinguish normal whisper. So I think there are it's a natural way to utilize this kind of abilities. So to summarize, so dual voice is using whisper voice as a command, and we created two types of neural networks, one for the voice recognition and the other for the classification, and we provide some applications. And this is the part of our bigger vision, human AI integration. I presented at the UIST Vision back in 2019. So thank you very much, and I want to show some other last announcement is this is the end of my talk, and I want to show the Sony Computer Science Laboratory is open a new research laboratory in Kyoto, Japan, and we want to we have some research positions and also intern program. So if you are interested in, please consult this URL. So the Sony CS Kyoto is very smooth laboratory and basically for the high-tech laboratory, but we want to provide more natural integration of human culture or affluence of the human life and also technology. So if you are interested, please visit this site. Thank you very much.
I was about to say thank you for the great presentation. Any question? So,
thank you much for the quick presentation. I really enjoyed your panel here. So I'm SIGCHI from Stony Brook University. So I feel like you really create a new modality in addition to regular speech. In your text editing example, you use whisper to input symbols. I wonder actually in text editing, sometimes you're also able to infer whether you want to input symbol or actual text. For example, your double quotation mark. If it's in the middle of a sentence, very likely it could be a symbol rather than the words. I'm wondering, have you considered taking into account the inference from the language context, combining it with your whisper to infer whether it's a symbol or text, because whisper might make mistakes sometimes.
Thank you very much. So actually, the existing text input like Google Doc, Google Speech also have ability to distinguish comma based on the context. So this is I think the one way to distinguish.
But I think the whisper is another way to distinguish normal and command. So maybe it's not limited to the separate to two technologies. Maybe you can combine. So by using normal single touch, so you can create a lot of input interaction technique. But if you allow to use a multi-touch, so there are a lot of more opportunity. But it includes a single touch. So I think this can be combined. Thank you very much.
Thank you. That was a great talk. I'm Yudai Tanaka from University of Chicago. I have a very simple question about how much cognitive load would be involved in switching between two modes of speech, like normal speech and whisper speech. Like
Yeah. So you can try. Actually, I feel that there's small amount of cognitive maybe load because yes. So maybe some training. But I think I found that it's much easier than shifting by physical load. So I think the synchronizing your speech act and other act like pushing is rather difficult. So I think like speech is an easy way. Thank you.
Hi, Jun. This is Pinyin. I just want to say how much I appreciate you have a single author paper and really remind us how the most elegant solutions sometimes are the easiest and keep pushing the creativity boundary. So on that note, have you considered combining, for example, facial expression? I show a smiley face and sad face as I'm talking, or combining other kind of characteristics of voice. I could rap. I could, I don't know, slow down if I'm trying to...
Yes. And there's important previous work by Masataka Goto is using the pitch of the voice. So you can say. It's also another way to distinguish the two modes. Or maybe so the facial expression or other nonverbal information can be incorporated. So thank you very much.
Thank you.
Hi, my name is Matt Fairland from the University of Calgary. I honestly had a question super similar to hers. So I was thinking about other input modalities like, I don't know, raising your voice instead or sounding angry. But I guess that's what you just said about pitch. So
Yeah. So I think whisper is one method for the distinguish two mode. So there are a lot of other opportunity. Like I think the previous research like this can be also separated. So the voice feature can be different. So
do you think wearing a mask and not wearing a mask has enough of like
Yeah.
difference maybe?
Yeah, I think so.
Oh, okay.
Yeah.
Cool. Thank you so much.
Thank you very much.
Really excellent. Thank you so much.
Also, I have some postcard for the Sony CSS Kyoto. If you want to, please take.
Yeah, let's get another round of applause for Jun. Thank you so much. And we will have our last presentation. The name is Photographic Lighting Design with Photographer in the Loop based on optimization. Actually, they also had a demo on Monday night.
Yep.
It's really great. I tried it and I liked it a lot. So I'm looking forward to more details about the paper. So the presenter will be Kenta Yamamoto from the University of Tsukuba. So take it away.
Yep. Thank you. Hello, everybody. I'm Kenta Yamamoto, a PhD student from University of Tsukuba Digital Nature Group in Japan. I will introduce our research of photographic lighting design with photographer in the loop Bayesian optimization. Traditionally, people have to manually adjust the lighting devices for the good lit photographs. However, it's difficult for the non-expert users and takes a very heavy process and much time. Therefore, we propose a novel design framework without manual adjustment. In our framework, photographers can focus on the lighting result with checking capture. Lighting design is a well-known task, and there have been many studies, not only for the actual photography, but also for the computer graphics. For example, in the computer graphics, there have been so many studies for the lighting design interfaces. On the left side, the research is about the painting interface for the lighting design. And on the right side, It's about the direct manipulation interface for the lighting design. But our research targets real-world lighting for the photography with various lighting devices. Next is about the lighting for the actual photography. In this slide, automatic lighting methods are depicted. On the left side, the automatic drone lighting is realized for the rim lighting. On the left and on the right side, the automatic flash lighting is realized for the good portrait lighting. But our goal is interactive frameworks that reflect photographers' preferences. Unlike these studies, this research aims to support the user's design process of portrait lighting. This research is the same as ours in the viewpoint of focusing on the capture time supporting system. However, we want to manipulate various lighting devices and take a human-in-the-loop approach. Finally, we introduced the relighting technology. Based on the improvement of the deep neural network, more accurate lighting is realized now. However, this technique is the post-processing method and cannot avoid from artifacts. We want to support the photographer as a capturing time, so this technique is started from different motivation. So let's move to our proposed framework. Our framework has two parts. One is for the photographer and the other is for the system. In the photographer part, the user selects the best one from the presented candidates and paints for the rough guiding. In the system part, the system searches next options based on the user's selection and painting. We define this looping process as photographer in the loop process. This research is defined as one of the human in the loop design optimization. In this optimization, humans are evaluators having perceptual objective function. Design optimization can be defined as a parameter optimization. For example, there is the arrangement task of a photograph enhancement. The number of sliders is the dimension of the input variables, and the user searches the optimal parameter set of them. In our case, design optimization problem is formulated as follows. Lighting design can be also defined as a parameter optimization problem. Lighting parameters X can be defined as follows, and we define the user preferences as the objective function. Here we call goodness function Gx. We want to solve the following optimization problem of Cx. And for the parameter optimization, Bayesian optimization is well known as the sample efficient parameter search method. BO can be applied to the black box objective function. However, it assumes that we can observe the absolute values of the black box function. So standard BO cannot be applied directly to the human in the loop design optimization because humans are not good at answering absolute values associated with input parameters. Then, for the human in the loop design optimization, instead of getting absolute values, relative comparison data are used. It's called preferential Bayesian optimization. For the comparison with multiple options, we adopt Bradley-Taylor-Lewis models as follows. We infer the values of Gx by map estimation using this model. So we formulated the lighting design problem, but we cannot directly solve this optimization problem because Gx is a black box function. In Bayesian optimization, acquisition function A is used to determine the next samples in each iteration. The acquisition function balances the exploration and the exploitation. These three images show how the parameter search progresses according to the selection results. Next is PBO with paint-based guidance. If the user selection information is only used, The standard acquisition function is enough. However, for using the user's rough painting as an additional guidance, we introduce advanced acquisition function. Our acquisition function is the extended version of Chen et al. 2021. A new term for the guide painting, G, is added, and W balances how much emphasis is given to the standard acquisition function and the paint guide. To optimize for the new acquisition function, we need to evaluate IX for arbitrary X. However, physically taking a photo each time takes too much time and is not differentiable. So we utilize lighting prediction technique. We adopt Gaussian process regressor as a differentiable lighting prediction method. It is one of the sample-based prediction methods. To train this regression model, we gather training data by automatically taking photos with random variables beforehand. Yeah, it takes less than 10 minutes. So now looking back at the overall workflow, first, training data is captured for the lighting prediction and the regressor is constructed. Second, initial random lighting configuration for the first iteration is captured. Third, the user selects best one and adds painting guide. Finally, the system searches next options using Bayesian optimization. Here, I demonstrate should be in the simulated virtual environment. Physical environment demonstration was done the day before yesterday at the demo booth. So, yes, get ready. Firstly, we can get random generated candidates. There is 4 options, and I chose the best one for me, this one, and I will add the paint for the highlight. After that, optimization process is running, and yes. Yes, the left side is last choice at the first iteration, and the rest of 3 present next iteration. And after that, adding a shadow. Yeah, shadow is added here, and there is highlighted. So go back to the presentation. Yes. Finally, I will show you the result and evaluation. We have design sessions results under the various conditions, such as the dimension of the input variables, various lighting parameters, simulation of physical environment, and so on. We can see how the lighting result candidates change according to the selections and paintings. We also have the technical evaluation results. In the technical evaluation, we prepared 3 conditions: random search, without painting, and with painting. All condition is trying to reach target image. However, painting can get closer to the target image with fewer iterations. We also conducted the user study with 12 participants. We prepared 2 types of the framework for the photographic lighting design. In all questions, our proposed framework was evaluated better than the traditional framework. Especially question 1 is the most important question for the validation of our contributions. It's indicated that people can become focusing on the designing task without handling lighting devices. There are many topics to discuss: users' limitation, higher dimensionality, accuracy of lighting diffraction, and so on. In the future, these problems and discussion points will be solved. Thank you for your attention.
Any question from the audience? Okay, I can start with mine.
Okay.
Thank you for the great presentation. So I'm curious about for a user, how many iterations they will work with the system. Actually, I think that could be dependent on the target, but I'm curious about the willingness of user to iterate.
Yeah, the number of iterations depends on the dimension of input variables. In the technical evaluation, for example, 3-dimensional input variables, few iteration is enough. And in our user study, 8-dimensional input variables are prepared, and in this user studies, many people are satisfied with 5 or 6 iterations. So not our framework doesn't need not too much iterations. Maybe less than 10 iterations.
Got it, thank you. So let's thank you again, and I think this is the end of this session. Thank you, everyone.